Good evening. You've arrived at the Earth Vault, a quiet space where Earth, science, nature, history, and philosophy meet, to guide you gently into rest. Here we don't chase the present. We drift, through time, through stone, through silence, to explore the ancient stories beneath our feet. Each episode is a slow descent into deep time and deeper thought. Let your shoulders drop. Let your breath soften. You are safe here. Have you ever asked yourself what the planet looked like before oceans had names? Before there were borders, mountains, or even the idea of continents? What was Earth like during Pangaea, when all the land on our planet was fused into a single, endless supercontinent? It might sound like fantasy, but it's rooted in some of the most compelling discoveries in geology. A time when the world was simpler, yet far more extreme. When North America nestled against Europe, and Africa was just a stone's throw from Brazil. A time when a creature could walk from what is now China to what is now Chile, without ever crossing a sea. Close your eyes for a moment. Picture a land without nations. No lights. No roads. Only forests, wind, and the low hum of volcanoes. Above, dragonflies with meter-wide wings drift through humid skies. Below, rivers carve endless paths across a massive, silent land. The planet breathes differently here. It feels unfamiliar yet deeply alive. Scientists call this ancient land Pangaea, and they believe it formed around 300 million years ago, in a slow-motion collision of tectonic plates. A dance of stone driven by the heat beneath the Earth's crust. But that's just one chapter. Geologists debate the rest. How many times has the planet gathered itself into one body, only to break apart again? This is part of what they call the supercontinent cycle. A process that continues even now, beneath your city, your home, your pillow. And so, wherever you are, perhaps you're listening from San Francisco, or Oslo, or Cape Town. Take a deep breath. Inhale history. Exhale the noise. Tonight, you won't just fall asleep. You'll fall backward, through millennia, into a world both alien and familiar. We're about to begin. Close your eyes for a moment and imagine a world without the borders we know today, a world where the lines on maps have no meaning, and the oceans we take for granted as separating continents do not exist. Hundreds of millions of years ago, Earth looked profoundly different. A single, uninterrupted landmass sprawled across the globe, unbroken and immense, stretching from the polar reaches of the north to the frozen edges of the south. This was Pangaea, a supercontinent that brought together nearly every landmass we now call continents, encircled by a vast, endless ocean known as Pangaea, a water body so immense that its horizon seemed to melt into the sky itself. Imagine standing anywhere upon this ancient land. Your gaze would sweep across plains, mountain ranges, deserts, and forests, uninterrupted by the rivers, bays, or coastlines that fragment our modern view of Earth. The sun would cast long shadows over undulating hills, illuminating red sandstone cliffs and the glint of crystal-clear lakes, while the wind whispered across vast interiors, carrying the scent of damp vegetation, parched soil, and distant salty seas. The air itself seemed more substantial, a gentle weight pressing softly against your skin, hinting at the breadth and scale of the world beneath your feet. Beneath this surface, the planet was far from still. The lithosphere, divided into immense tectonic plates, moved imperceptibly yet inexorably, grinding, colliding, and merging to shape the land over millions of years. Mountains rose and fell like frozen waves, vast ranges folding upon themselves with a slow majesty almost impossible to witness in a human lifetime. The Appalachians in North America, the Anti-Atlas in Morocco, the Caledonian chain stretching across what is now northern Europe. These are remnants of these ancient processes, their origins lost to time yet whispered in the stones themselves. The plates carried vast tracts of land, North America, Europe, Africa, South America, India, and Australia, into an intimate embrace, fusing them into a single, continuous expanse where creatures could wander freely across thousands of kilometers without ever touching the waters that would later divide them. Pangaea, though magnificent, was not the first supercontinent. Rodinia and Pannotia predated it, offering a reminder that Earth's surface is a stage for repeated cycles of unity and division, of collision and dispersion. The interiors of Pangaea were realms of extremes. Far from the calming influence of the surrounding Panthalassa, immense deserts baked under a relentless sun, their surfaces cracked and fissured, dust rising in slow, golden clouds that shimmered in the faint heat haze. Summers scorched the soil to a deep, rusty red, while winters brought biting cold, a stark reminder that without the moderating effect of ocean currents, climate could be unforgiving. Winds swept unbroken across the land, carrying fine sand and ancient spores from one end of the supercontinent to the other, creating ephemeral, shifting patterns on the desert floor. In contrast, the coasts were cradled by ocean moisture, rich with swamps, wetlands, and primitive forests. Gigantic tree ferns stretched skyward, forming dense canopies, their leaves dripping with condensation from nightly fogs. Early amphibians thrived here, finding sanctuary in pools and streams, while reptiles, experimenting with life beyond water, slowly colonized drier interiors, exploring niches that would ultimately shape the evolutionary paths of terrestrial life. Giant insects filled the air with a low, hypnotic hum. Dragonflies with wings spanning nearly a meter hovered above rivers, their delicate movements almost ethereal as sunlight danced across membranous wings. Beetles the size of modern birds scuttled across logs and fallen leaves, armored and glossy, while other arthropods tunneled beneath the rich humus, unseen but integral to the ecosystem. High oxygen levels in the late Carboniferous, reaching perhaps 30%, enabled these remarkable sizes, a stark reminder of how chemistry and life are interlinked, how the very composition of the air can dictate what forms life may take. Even today, scientists debate the precise mechanisms behind these oxygen fluctuations, yet the fossil record leaves no ambiguity. Life in Pangaea flourished in astonishing diversity and scale. Rivers served as the arteries of this great land. Some flowed uninterrupted for thousands of kilometers, their waters nourishing forests and wetlands, connecting ecosystems that would now be oceans apart. The winds, unobstructed by modern mountain chains, swept in constant, steady flows, carrying moisture inland, dust across plains, and even the smallest seeds across vast distances. Panthalassa, the global ocean encircling this supercontinent, lapped at distant shores, its rhythmic waves both soothing and commanding, a reminder that the planet's systems were vast and interconnected. Volcanic activity punctuated the landscape, a quiet yet persistent heartbeat beneath the surface. In some regions, gentle eruptions created fertile soils and rolling volcanic hills. In others, massive plumes of lava and ash heralded dramatic changes, shaping mountains and altering climates. The Siberian traps, though occurring later, offer a preview of how concentrated volcanic activity could affect the planet on a global scale, linked to mass extinctions that reset ecosystems entirely. Even amidst these cataclysms, life persisted, small but resilient synapsids and other creatures finding niches, adapting, surviving. The earth itself seemed alive, breathing through its mountains, rivers, and winds, pulsing with a quiet, patient rhythm of geologic time. Across Pangaea, evolution experimented on a continental scale. Amphibians dominated the wet margins, reptiles expanded into drier regions, enormous insects patrolled the skies, and early forests sprawled in humid belts, forming the first major coal swamps. Life was free to disperse without the obstruction of oceans, evidenced by fossils found today on continents now separated by thousands of kilometers. This single, unified landmass created both opportunity and challenge, shaping survival strategies, driving adaptation, and setting the stage for future radiations of species, including the dinosaurs and mammals that would follow. Scientists still debate the exact dispersal routes, the influence of climatic oscillations, and how certain species achieved such widespread ranges. Pause. Take a slow breath. Imagine yourself standing in a central plain of Pangaea, feeling the warmth of the afternoon sun, the caress of a distant breeze, the faint hum of dragonflies and insects nearby. Watch the slow sway of giant ferns, hear the trickle of rivers stretching beyond the horizon, sense the subtle vibration of the earth beneath your feet, as if the planet itself were breathing, pulsing gently in time with life above. See the mountains in the distance, their jagged peaks reaching toward the sky, and know that these ranges were formed through collisions of continental plates over tens of millions of years, each centimeter of uplift a testament to Earth's persistent dynamism. The unity of Pangaea was impermanent, a moment in a continuous cycle of assembly and breakup. Beneath its surface, heat built up in the mantle, plates strained, and fissures appeared, foreshadowing the eventual rifting that would separate North America from Africa, fragment Gondwana, and carve new oceans that would redefine climates and ecosystems. Yet even in its fleeting existence, Pangaea left a legacy etched in mountains, sedimentary layers, fossil distributions, and even the genetic memory of organisms. Its story is embedded in the very structure of the Earth, reminding us that the planet is a living, ever-changing system, vast in scale and astonishing in resilience. Breathe deeply again. Let the wind carry your imagination across deserts, rivers, and forests. Hear the whisper of water, the murmur of leaves, the distant hum of insects, the low rumble of volcanoes. Picture the supercontinent as a single organism, alive and interconnected, every river a vein, every forest a lung, every mountain a heartbeat. Allow this vision to sink into your mind, a gentle lullaby of Earth's history, as we prepare to journey deeper into the forces, climates, and life forms that shaped Pangaea, stepping slowly, reverently into the story of a world once whole, a world that still speaks to us through stone, air, and memory. Here begins our exploration of Earth when it was one, a continent unified, a global ocean endless, life diverse and unbounded, and the rhythms of the planet vast and patient. As we follow the slow dance of plates, the meandering rivers, the forests that stretched for hundreds of kilometers, and the creatures that roamed this immense land, let your mind wander and settle, letting each detail of Pangaea's vastness echo in your imagination, preparing you to drift further into the depths of Earth's ancient, dreamlike history. Imagine the Earth not as a static globe, but as a living, breathing body, its surface floating atop a molten underworld, a thick, flowing mantle that pulses with heat and energy. Beneath the crust, temperatures reach thousands of degrees, and this searing warmth drives the slow but inexorable motion of tectonic plates. These massive slabs of lithosphere, some hundreds of kilometers thick and spanning continents, drift across the surface in a dance that takes millions of years to complete, imperceptible in a human lifetime yet monumental on the scale of geological time. Every collision, every subduction, every divergence of plates shapes the very face of our planet, lifting mountain ranges, carving valleys, and opening vast oceans. Imagine standing on the edge of an emerging range, the rocks beneath your feet still vibrating with heat from the mantle below, sensing the tremendous power that moves silently yet persistently beneath you. Before Pangaea ever existed, the Earth had seen earlier supercontinents, each forming and breaking apart in cycles of creation and destruction that geologists term the supercontinent cycle. Rodinia, for instance, emerged over 1 billion years ago, a precursor to the later configurations, bringing together almost all of the Earth's continental masses into a unified landmass. Picture Rodinia as an embryonic Pangaea, its boundaries still fluid, its interiors reshaped by slow-motion collisions, mountain building and mantle-driven convection. The assembly of such a supercontinent is not an instantaneous event but a slow choreography. Continents drift, gently approach one another, collide in subtle increments measured in centimeters per year, compressing crust into towering ranges, folding strata into complex patterns, and creating rift zones where the land might one day split apart again. Even the simplest hill or valley is a testament to this immense timescale, a reminder that Earth's surface is far from still. Following Rodinia's eventual fragmentation, Earth witnessed the brief existence of Pangaea, a supercontinent that formed roughly 600 million years ago. Pangaea's story was fleeting yet significant. It set the stage for the assembly of later continents by reorganizing land masses, redistributing ocean basins and altering global climate patterns. As you visualize Pangaea, imagine a world in flux, plates shifting like pieces of a slow-moving puzzle, oceans shrinking and expanding and mantle currents channeling heat in complex, three-dimensional flows. These currents act as Earth's hidden engine, rising as plumes of buoyant, heated rock that can uplift surface regions or fracture lithosphere, initiating rifts that may one day birth oceans. Even today, scientists continue to investigate the precise behavior of mantle convection, debating the scale and influence of deep mantle plumes versus shallow plate-driven flow. What remains clear is that the energy stored in Earth's interior is both subtle and profound, capable of shaping entire continents over eons. Consider the mechanics of this slow dance. Subduction zones, where one plate slides beneath another, act as massive conveyor belts, recycling oceanic crust back into the mantle, creating earthquakes, volcanic arcs, and mountain chains. Rift zones, conversely, are sites of divergence, where plates pull apart, allowing molten material from below to rise, forming new crust, mid-ocean ridges, and eventually ocean basins. Each plate is guided by forces both gravitational and thermal. The cooling of old lithosphere, the buoyancy of hot mantle plumes, and the pull of dense, sinking slabs all contribute to a complex, slow-motion ballet. Imagine the patience of time itself as the continents inch together and apart, mountain ranges folding, basins deepening, and oceans expanding over tens to hundreds of millions of years, their transformations imperceptible in a single human lifetime but monumental when viewed in the arc of Earth's history. During the late Precambrian and early Paleozoic, the assembly of these supercontinents was accompanied by dramatic geological and climatic effects. As Rodinia coalesced, its interior became arid and subjected to extreme temperature fluctuations, far from the tempering influence of the ocean. Pangaea's brief existence altered ocean currents and sea levels, influencing early marine life and sedimentation patterns. The supercontinent cycle also affected atmospheric composition. Large continental interiors limited evaporation, creating deserts, while volcanic activity associated with plate collisions and mantle plumes released gases into the atmosphere, subtly shifting climate and oxygen levels. Picture ancient landscapes where rivers struggled to flow across vast dry plains, mountain ranges created rain shadows, and coastal zones teemed with shallow seas. Each environment, shaped by plate motion, created niches for life to adapt, evolve, and thrive in surprising ways. One fascinating aspect of plate tectonics is how it leaves tangible clues across modern continents. Mountain belts like the Appalachians in North America and the Anti-Atlas in Morocco share ancient roots, remnants of collisions during Rodinia's formation. Rocks found in one continent often match in age, composition, and structure with those on a distant landmass now separated by thousands of kilometers of ocean. Fossils, too, tell a similar story. Identical species appearing on continents now distant provide a living record of past connectivity. Yet even as we uncover these connections, Scientists continue to debate the exact positions, timings, and processes that govern supercontinent assembly, highlighting the ongoing intrigue and mystery of deep Earth processes. Visualize standing atop a high plateau of Rodinia, gazing across plains stretching beyond your sight, knowing that millions of years later, these same lands will drift apart, forming Pangaea, and eventually coalescing into Pangaea. Imagine the heat of the mantle below radiating faintly through the rocks, a gentle reminder of the planet's interior energy, and the slow, almost imperceptible motion of your ground beneath, as if Earth itself were breathing, moving in rhythms far beyond human perception. Across this expanse, rivers would carve valleys over millennia, winds would shape dunes and distribute seeds, and life, tiny and evolving, would take hold, influenced subtly by these shifting geological forces. Mantle plumes occasionally rise in buoyant columns, forming hotspots that create volcanic chains visible for hundreds of kilometers, sometimes forming islands and reshaping coastlines long before humans existed. These thermal anomalies are thought to play a key role in continental breakup, weakening lithosphere and initiating rifting. The exact mechanisms remain debated. Do plumes drive plate movement, or do plates passively respond to deeper mantle convection? Such questions remind us that Earth's interior remains only partially understood, yet the evidence of its immense power is etched in every ridge, canyon, and volcanic plateau. The dance of plates is patient and precise. Imagine billions of years condensed into a slow-motion ballet. Continents drifting, colliding, folding, and fracturing, oceans shrinking and expanding, mountains rising slowly, rivers carving valleys with gentle persistence, life adapting and radiating across ever-changing landscapes. Every mountain, every valley, every ancient rock formation is a note in this symphony of motion, a reminder that the earth beneath our feet is dynamic, alive, and constantly reshaping itself. The legacies of Rodinia and Pangaea, though long gone, are still visible in the fractures, folds, and fossil patterns that pepper the modern world, echoing the rhythm of a slow, magnificent dance that continues today beneath our feet. Take a deep breath. Imagine the heat of the mantle beneath, the gentle hum of Earth's deep energy, the inexorable motion of plates carrying continents like dancers across a stage measured in millions of years. Feel the subtle rise of mountains, the widening of valleys, the expansion of oceans. Sense how these movements not only reshape land but also influence climate, ocean currents, and life itself. Let your mind drift across Rodinia, Pangaea, and Pangaea, following the patient rhythm of tectonic forces, the unseen heartbeat of the planet, and allow the enormity of this slow dance to fill your imagination with awe and tranquility. As the Earth continues this slow, powerful dance, we begin to understand that the continents we know today are temporary guests atop a restless mantle, and that each cycle of supercontinent assembly and breakup leaves lasting imprints on climate, ecosystems, and the very evolution of life. With this vision in mind, let your imagination wander across the slow-motion movements of plates, the heat rising from deep below, and the grand rhythm of Earth's tectonic ballet, as we prepare to explore how this dance shaped Pangaea into the supercontinent that would dominate our planet for millions of years. Picture standing in the center of Pangaea, far from any ocean's moderating touch, under a sky so vast and empty that it feels infinite. The sun blazes overhead in a relentless arc, casting the central plains into a furnace of heat that would make a modern desert seem mild by comparison. This is the heart of the supercontinent, a sprawling expanse of arid land stretching for thousands of kilometers, where rainfall is a rare gift, and the air shimmers with the heat rising from the parched surface. Sand and rock dominate this interior, painted in ochres, deep reds, and burnt siennas, the colors of ancient deserts frozen in stone layers that geologists will one day uncover. During summer, temperatures soar to extremes, baking the crust and forcing any life to adapt to brutal heat. while winter brings a chilling reversal, where icy winds sweep across these endless plains, turning the sand and stone into a brittle landscape, echoing with the distant calls of early reptiles or winged insects. Pangaea's vastness meant that it spanned multiple climate zones, a single landmass stretching across the equator and deep into polar latitudes. At the equatorial heart, broad tropical belts captured intense solar energy, fueling monsoons and seasonal rains that attempted in vain to penetrate the inland deserts. These winds carried moisture from distant coasts, only to deposit fleeting showers upon the thirsty sands before vanishing into the heat. Here one can imagine towering dust storms rolling across the plains, casting an orange haze over the horizon, while giant insects buzzed tirelessly in the oxygen-rich atmosphere, tracing invisible paths above the cracked earth. Scientists still debate the precise intensity of these monsoonal patterns, but it is clear that the central deserts of Pangaea were inhospitable, vast, and extreme, a testing ground for the resilience of life. Journeying north or south from the equatorial deserts, the landscape gradually shifts. The interior gradually softens under seasonal patterns, river valleys appear where water manages to carve channels through the crust, and vegetation begins to dot the landscape. Along coastal regions, the moderating influence of the Pangaea Ocean is evident. Humidity rises, rainfall becomes more consistent, and lush forests and extensive swamps flourish. Imagine dense ferns and towering primitive trees draping over the riverbanks, their roots sinking deep into nutrient-rich soil, while dragonflies with meter-wide wings skim across the still waters. Fossilized coal beds reveal these verdant expanses, evidence of the extraordinary productivity of life in regions buffered by the ocean. The dichotomy is striking. Harsh deserts in the heart, thriving, humid wetlands along the margins, a planet of contrasts unified within a single continental body. Venturing toward the poles, the extremes of Pangaea's climate become even more pronounced. The northern and southern reaches of the supercontinent extended deep into high latitudes, where sunlight varied dramatically with the seasons, and temperatures plummeted in the long winters. Despite this, life found niches to exploit. Polar forests emerged consisting of hardy gymnosperms and seed ferns adapted to cold and seasonal darkness. The flora and fauna of these regions evolved with remarkable ingenuity, exhibiting strategies for survival that would echo millions of years later in the temperate and boreal ecosystems we know today. Picture snow dusting the needles of ancient conifers, icy streams winding through frozen valleys, and the faint movement of amphibians and reptiles conserving energy in subterranean burrows during harsh winters. Even here, scientists note evidence of climatic fluctuation, and debates continue over how extensive these polar forests truly were and how they responded to glacial episodes. The southern supercontinent of Gondwana, forming the lower portion of Pangaea, tells a story of even more extreme contrasts. Vast ice sheets once covered large portions of this landmass, evidence preserved in striated rocks and glacial deposits scattered across modern-day South America, Africa, Antarctica, India, and Australia. These icy expanses were interspersed with temperate pockets along the coasts, where melting waters fed rivers and wetlands that nurtured early amphibians and seed plants. Imagine glaciers grinding across ancient bedrock, carving valleys and leaving polished scars, while nearby swamps and coastal forests buzzed with life in their own microclimates. The juxtaposition of ice and lush greenery demonstrates the dramatic gradients that existed on Pangaea and emphasizes how geography and latitude shaped climate and biodiversity. Inland deserts were not devoid of life entirely. Fossil evidence and sedimentary records indicate that specialized plants and small, pioneering animals adapted to extreme heat and aridity could eke out a precarious existence. Some of these species likely burrowed into the ground during the hottest periods, emerging to forage during cooler hours, or develop thick exoskeletons or waxy coatings to retain moisture. It is possible, scientists suggest, that early reptiles and amphibians used seasonal water holes as critical lifelines, congregating briefly before dispersing again across the vast terrain. These adaptations highlight the ingenuity of life, responding to harsh conditions that challenge survival, revealing patterns of evolution and ecology that continue to fascinate modern researchers. The monsoonal belts at the equator were themselves shaped by the sheer size of Pangaea. The vast interior created a thermal contrast with the surrounding oceans, intensifying seasonal winds and driving periodic floods in coastal regions. Picture a storm slowly rolling across the landscape, clouds gathering over a shimmering river delta, lightning illuminating distant forests, while inland deserts remain dry and still under the relentless sun. This interplay of heat and moisture produced complex weather systems, and in some areas wind-carved dunes carried sands across thousands of kilometers, depositing them in ephemeral basins where early life might find temporary refuge. Scientists continue to model these ancient climate systems, using computer simulations and sedimentary evidence to reconstruct rainfall patterns, seasonal extremes, and the migration of climatic belts across the supercontinent. Meanwhile, coastal wetlands were lush and teeming with biodiversity. Swamps, deltas, and estuaries provided refuges for aquatic and semi-aquatic life. Imagine towering horsetail plants and seed ferns shading shallow pools where amphibians breed, insects hum through humid air, and rivers slowly meander toward the ocean. These ecosystems stored carbon, enriched soils, and created conditions that would later leave behind coal beds, a testament to the productivity and resilience of life even on a planet of extremes. The juxtaposition between the arid deserts, the wet equatorial zones, and polar forests forms a tapestry of contrasts, illustrating that Pangaea was not a monolithic environment but a world of interwoven extremes, each region shaped by latitude, ocean proximity, and the movement of the underlying plates. Wind and weather also played a significant role in sculpting Pangaea's landscapes. Strong, unimpeded winds swept across vast deserts, eroding rock, shaping dunes, and transporting sediments to distant shores. Seasonal monsoons redistributed water and nutrients, influencing plant growth and sedimentation patterns, while coastal storms battered the edges of the supercontinent, carving cliffs, estuaries, and channels. The energy of these natural forces, wind, rain, temperature extremes, was a constant presence, a reminder of the dynamic interplay between climate and land that existed long before human observation. As you close your eyes and imagine Pangaea's climates, picture the contrasts: the relentless heat and dryness of equatorial deserts, the verdant, humid swamps along coasts, the snow-dusted forests at polar latitudes, and the giant glaciers carving Gondwana. Feel the wind on your skin, hear the distant rush of rivers, the crackling of dry sand underfoot, the buzzing of enormous insects, the whisper of seasonal monsoons. Imagine the supercontinent as a living, breathing entity, vast and extreme, yet unified, with each climate zone contributing to a delicate balance that shaped the evolution of life and laid the foundations for the ecosystems that would emerge in the future. Pangaea's climate was a story of extremes, of contrasts so stark they seem almost unreal. Yet it was precisely these extremes that drove adaptation, diversity, and the slow march of evolution. Every desert dune, every forested riverbank, every polar ice sheet was part of a vast planetary narrative, a stage upon which life experimented, persisted, and thrived in ways both familiar and alien to us. Scientists continued to explore these patterns, modeling temperatures, rainfall, and atmospheric circulation to understand how life endured and evolved under such dramatic conditions. The debate over the precise intensity of Pangaea's deserts, the size of monsoonal belts, and the extent of polar forests remains open, but the evidence is clear. Pangaea was a world of breathtaking extremes, a crucible for life, and a testament to Earth's capacity for variation and resilience. Take a moment. Breathe deeply. Let your imagination drift from the blazing deserts of the equator, through humid riverine forests, to snow-dusted polar landscapes. Feel the passage of time in the slow shifting of winds and seasons. Sense the pulse of rivers, and hear the faint whisper of ancient monsoons. Let these visions fill your mind as you journey through the climate extremes of Pangaea, allowing the stark beauty and incredible diversity of this ancient world to wash over you, slowly, gently, and completely. Imagine a world where the land stretches endlessly, unbroken by vast oceans or impassable seas. A single, continuous expanse of Earth, Pangaea, dominates the planet, its edges lapping against the global ocean panthalassa, yet within its massive interior life knows no barriers. From what would much later become North America, across Europe and Asia, down through Africa, to the southern reaches of Gondwana, animals and plants roam across a united landscape. The absence of modern oceanic divisions created a supercontinent where migration was not hindered by water, where species could traverse thousands of kilometers over generations, and where evolutionary paths intertwined in extraordinary ways. Consider a small reptile in what will one day be Central Europe. It can move northward into a land that will become Scandinavia, or westward into the heart of North America, following rivers, forests, and grasslands. Its descendants, 1,000,000 years later, may find themselves in the deserts of future Africa, adapting to new climates, new predators, and new sources of food. Similarly, enormous herbivorous creatures that evolved in central Gondwana could slowly disperse northward into temperate zones, encountering other species and triggering ecological interactions that would have been impossible on fragmented continents. Fossil evidence supports this. Identical or closely related species appear in locations that, millions of years later, are separated by vast oceans. For paleontologists, these fossils are a map of a vanished world without boundaries, a window into a planet where life was free to explore and diversify without the interruptions imposed by isolated continents. Without the division of oceans, the usual barriers to migration, the coasts, the deep water, the currents, disappear. Rivers carve their way through the landscape, connecting forests, swamps, and deserts. Mountain ranges provide both corridors and obstacles, channeling animal movements along valleys and passes, while vast plains serve as highways for species traveling in search of food, mates, or seasonal shelter. Imagine herds of early synapsids moving in long lines across endless plains, their movement unconstrained, leaving tracks in sediment that will fossilize for hundreds of millions of years. Birds and pterosaurs can traverse large areas without concern for water gaps. Reptiles crawl across shores and lowlands, while amphibians follow rivers and wetlands. Each species contributes to the intricate web of life, a network of migration, predation, and coexistence that is uniquely Pangaea's signature. This lack of boundaries had profound consequences for evolution. On smaller, isolated continents, species often evolve in isolation, adapting to their own restricted environments, leading to endemism, species found nowhere else. But in Pangaea, isolation was minimal and gene flow was extensive. Populations could mix across vast distances, sharing genetic material in ways that accelerated diversification. For example, the same amphibian lineage could spread from what is now North America into southern Europe, adapting to different climates but maintaining connections to its ancestral gene pool. Similarly, reptiles migrating from the equatorial interior into polar forests would carry with them traits shaped by arid lands, introducing adaptive variations that might affect competition, predation, or survival strategies. In a sense, Pangaea functioned as a vast evolutionary laboratory, a single, interconnected ecosystem stretching from pole to pole. The fossil record provides tantalizing glimpses of this phenomenon. Paleontologists have discovered fossilized remains of similar species on what would much later be separate continents. Dicynodonts in Africa, India, and South America. Early dinosaurs scattered across what is now North America, Europe, and Africa, and the seeds of primitive plants appearing in strata that stretch across the supercontinent. Each discovery reinforces the concept of a connected Pangaea, where species could roam freely and evolve in concert, with migration patterns shaping ecosystems over millions of years. Even subtle variations in morphology or size often reflect the adaptive pressures experienced in different regions of the same supercontinent, providing insight into the fluid interplay between geography and evolution. Consider the implications for ecosystems. Predators could follow prey across long distances, tracking migrations over thousands of kilometers. Herbivores could explore new feeding grounds, encountering different plant species and altering vegetation patterns along the way. Rivers, floodplains, and coastal wetlands served as conduits of biodiversity, connecting disparate habitats. The boundaries that once separated species, whether geographic or ecological, were diminished or removed entirely. The mixing of species encouraged competition, adaptation, and innovation in evolutionary strategies. Some species thrived, while others perished, leaving a dynamic and constantly changing mosaic of life across Pangaea. The absence of modern seas also meant that climatic and environmental shifts could ripple across enormous distances. A drought in the interior deserts might drive animals northward or southward in search of water, mixing populations that had previously remained separate. Similarly, the spread of lush equatorial forests along coasts could allow tropical species to expand their ranges, influencing distant ecosystems thousands of kilometers away. Every migration, every seasonal movement, every adaptation contributed to the complex tapestry of life, a web interconnected in ways that would be impossible on today's fragmented continents. From an evolutionary perspective, Pangaea's connectedness also facilitated the rise of some of Earth's earliest large terrestrial vertebrates. Massive herbivorous and carnivorous reptiles moved across the land, shaping vegetation and predation pressures over wide areas. Their movements left traces not only in fossils but in the very structure of ecosystems, influencing the distribution and evolution of smaller species. For example, herbivorous species feeding on coastal swamps and inland plains would disperse seeds, altering plant communities across thousands of kilometers. Predators following these prey species would inadvertently enforce natural selection, sculpting the survival of countless other organisms. But this world without boundaries was not uniform. Environmental gradients, from arid interiors to humid coasts, from equatorial warmth to polar cold, still imposed selective pressures. Species did not roam randomly. They followed pathways shaped by climate, topography, and resource availability. Yet, compared with a fragmented continental arrangement, the barriers were minimal. Evolutionary pressures were both local and global, producing lineages that were adaptable, versatile, and capable of extensive dispersal. It is a vision of life as a continuous, dynamic network, where boundaries are not defined by water or tectonic separation but by ecological opportunity and adaptation. Fossil evidence underscores this reality in vivid detail. Consider the genus Lystrosaurus, a dicynodont whose remains have been found across Africa, Antarctica, and Asia. This remarkable distribution reveals how a single species, or closely related species, could traverse thousands of kilometers, exploiting diverse environments and adapting to variable climates. Similarly, early archosaur fossils appear in strata spanning the northern and southern reaches of Pangaea, demonstrating long-distance dispersal and a remarkable capacity for ecological flexibility. Each fossil discovery is a testament to the absence of geographic boundaries and a reminder of the supercontinent's unique evolutionary context. Even plant life benefited from the lack of boundaries. Ferns, seed ferns, and early gymnosperms could colonize wide swathes of the supercontinent, spreading spores and seeds over vast distances without interruption. Coastal wetlands, river valleys, and even arid regions acted as conduits for plant dispersal, allowing the creation of connected biomes. The interactions between plants and animals were equally unhindered. Herbivores could shape vegetation patterns, while predators and scavengers influenced herbivore populations over expansive ranges. Ecological networks formed on continental scales, illustrating the interconnectedness of life in Pangaea. In this continuous landmass, evolutionary innovation thrived. Species that might otherwise have been confined to isolated pockets now had opportunities to interact, compete, and hybridize across great distances. The genetic diversity maintained by these movements strengthened populations, allowing adaptation to climatic fluctuations, disease pressures, and ecological shifts. Over millions of years, this process produced complex ecosystems where species were both specialists and generalists, adapted to local conditions yet capable of thriving across multiple regions. Finally, reflect on the temporal scale. Pangaea persisted for tens of millions of years, long enough for these patterns of migration and evolution to leave indelible marks on the fossil record. Each fossil, each sedimentary layer, each coal seam is a fragment of this story, a narrative of life free to roam, to adapt, to intermingle without the divisions that modern oceans impose. The supercontinent was not merely a static landmass, it was a dynamic stage, a sprawling evolutionary theater where the drama of life unfolded uninterrupted, shaping the diversity of species and ecosystems that would eventually populate fragmented continents after Pangaea's eventual breakup. Take a moment to imagine walking across this world. Feel the wind across endless plains, hear the rustle of ferns in equatorial wetlands, watch a herd of early herbivores migrate along a river valley, and glimpse the shadow of a predator in pursuit. Picture the seamless land stretching thousands of kilometers, connecting polar forests, deserts, tropical swamps, and coastal plains. Every step you take is part of a living network, a planet without boundaries, where evolution is a shared experience across space and time. Fossils may remain as the only tangible evidence for us today, yet they speak eloquently. This was a world of free movement, of interconnected species, and of evolutionary innovation unrestrained by the oceans that would one day fragment it. Pangaea, in essence, was a canvas for life to roam without restriction. It was a continent of possibilities, a stage for evolution, and a testament to the power of a world without boundaries. The lessons it imparts resonate today, reminding us that connectivity, whether of ecosystems, species, or even ideas, is a driver of resilience, adaptation, and transformation. Close your eyes and imagine a Pangaean landscape stretching endlessly before you. Vast plains extend toward distant mountain ranges, deserts flare beneath an unrelenting sun, and thick forests sway along distant coasts. Above it all, the wind moves freely, unshackled by oceans, following invisible pathways across thousands of kilometers. On this supercontinent, the air itself is a conveyor of memory, carrying the stories of climates, seasons, and distant landscapes, and shaping life in ways that resonate across space and time. The winds do not bend around continents as they do today. They sweep across the entirety of Pangaea, their influence reaching from the tropical equator to the icy poles. These vast currents sculpt not only the climate but the ecology, the vegetation, and even the evolution of species that live upon this enormous landmass. Because the supercontinent is a single, unbroken expanse, air masses originating over deserts in the interior have the freedom to travel unimpeded to coastal forests and equatorial wetlands. Imagine a hot, dry wind lifting fine sand and dust from the central deserts and carrying it hundreds, even thousands of kilometers, depositing nutrients into fertile river valleys and coastal plains. Such movement forms a natural cycle, connecting the interior to the margins of the continent. Sediments and organic materials carried by these winds enrich soils far from their source, providing the basis for dense forests and thriving wetlands along the coastlines. In this way, the winds act as unseen gardeners, fertilizing distant lands and maintaining ecological continuity across Pangaea's vast expanse. These winds are not merely passive carriers of dust. They are powerful agents in the shaping of climate. Seasonal monsoons arise with rhythmic regularity, driven by the juxtaposition of scorching interior deserts and the relatively cooler margins along the equator. During certain times of the year, winds reverse direction, bringing moist air from the coasts into the interior, triggering short-lived but intense periods of rainfall that revitalize parched landscapes. These monsoonal cycles create a dance between wet and dry, fostering adaptations in plants and animals alike. Herbivorous reptiles in the central deserts must endure extreme dry spells, while those near rivers and wetlands exploit the brief abundance of resources brought by the seasonal rains. The interplay of wind and water sculpts the supercontinent's living fabric, generating ecological patterns that are entirely unique to a world without oceanic interruptions. Beneath this aerial choreography, the veins of water carve their way across Pangaea. The rivers of this supercontinent are unlike anything we see today. They are colossal in scale, some stretching thousands of kilometers, linking highlands to lowlands, mountains to plains, deserts to coasts. These rivers are the supercontinent's arteries, channels through which life circulates and ecosystems connect. From the peaks of ancient ranges to the distant margins of Pangaea, rivers transport not only water but nutrients, sediments, and living organisms. They serve as highways for fish, amphibians, and aquatic plants, while providing critical watering holes for land-dwelling creatures that migrate along their banks. Consider a river that begins in a northern mountain range and flows steadily southward for thousands of kilometers. Along its path, it collects tributaries, widening and deepening, creating floodplains rich in fertile silt. Amphibians breed in its shallow waters, reptiles bask on its banks, insects swarm above its surface. Birds and pterosaurs follow its course, nesting in nearby forests or hunting along its banks. These rivers are living corridors, threading together disparate habitats, enabling species to disperse, colonize, and interact across massive distances. In the absence of oceanic barriers, these fluvial networks are essential for the movement and survival of life, acting as lifelines for organisms in otherwise inhospitable interior regions. The river systems of Pangaea are intimately tied to the winds above. Seasonal rains swell river volumes, transforming narrow streams into roaring currents, inundating floodplains and replenishing wetlands. Conversely, winds can dry river surfaces, exposing sandbars and creating temporary barriers to movement, forcing species to adapt, migrate, or hibernate. These intertwined patterns of wind and water create dynamic landscapes, shifting over time, yet providing consistent pathways that life can exploit. Over millions of years, these rivers sculpt valleys, carve canyons, and deposit sediment across plains, leaving behind geological fingerprints that paleontologists and geologists use to reconstruct Pangaea's lost world. The scale of these rivers is staggering. Some may have rivaled the Amazon or Nile of modern times, yet they span entire latitudinal zones, traversing deserts, mountains, and forests alike. Tributaries branch into labyrinthine networks, connecting distant regions in ways unimaginable on today's fragmented continents. They offer refuge and sustenance during dry periods, linking populations of species otherwise separated by vast inhospitable landscapes. Fish and amphibians, carried by these waterways, disperse to new regions, spreading genetic material across the supercontinent and facilitating evolutionary connections that cross ecological boundaries. The rivers themselves become conduits for life, memories of water echoing across time and space. Alongside rivers and winds, lakes and inland seas punctuate the supercontinent, amplifying the effects of water on ecosystems. Shallow basins collect rainfall, creating temporary oases in otherwise arid interiors. These bodies of water serve as critical breeding grounds for aquatic organisms, while attracting herbivores and predators alike. Seasonal fluctuations in water levels, driven by both wind and precipitation patterns, shape the distribution and behavior of species. Plant life flourishes along margins, forming riparian forests that provide shelter, food, and nesting grounds. These inland waters are microcosms of interconnected life, miniature hubs that feed into the grand vascular system of Pangaea's rivers. Wind and water together produce a striking mosaic of environments. Coastal forests thrive on nutrients deposited by both riverine sediment and airborne dust, while interior deserts remain arid, shaped by persistent winds that drain moisture from the soil. Seasonal monsoons dictate flowering and fruiting cycles, influencing the migration patterns of herbivores. Rivers flood to redistribute nutrients, then reseed, leaving behind fertile plains that will sustain generations of terrestrial life. Life in Pangaea is thus a story of adaptation to the rhythms of wind and water, a narrative written in sediment, silt, and the flowing of rivers. Fossilized sediments bear testimony to these ancient rivers and wind patterns. Cross-bedded sandstones indicate the directions of massive desert winds, while layers of silt and clay reveal the seasonal floods of mighty rivers. Fossilized plant debris, spores, and pollen found in distant regions testify to the wind's ability to transport life across thousands of kilometers. Similarly, fossilized aquatic organisms demonstrate the continuity of river systems, revealing the passage of species from one habitat to another over immense distances. By tracing these records, scientists reconstruct the memory of Pangaea's winds and the veins of its rivers, revealing a supercontinent alive with motion, interconnectedness, and ecological complexity. Consider how these rivers shape evolution. Populations along major river systems are constantly connected yet spatially varied, creating opportunities for both local adaptation and long-distance dispersal. Genetic material spreads along the waterways, creating populations with a mix of traits suited for different climates, soils, and vegetation. Predator-prey relationships are influenced by river corridors. Herbivores follow seasonal flows to new feeding grounds, while predators track their movement. Plants rely on water to disperse seeds, ensuring that vegetation communities are dynamic and interconnected. Over millions of years, this interaction of wind, water, and life produces a living supercontinent where evolution is a grand, interconnected symphony. The winds themselves leave marks beyond ecology. Dust carried from the interior deserts fertilizes coastal forests, enhances soil productivity, and even influences climate by altering atmospheric opacity and solar radiation. Seasonal monsoons, driven by the temperature contrast between interior deserts and coastal regions, regulate river flows and dictate rainfall patterns. Together, wind and water dictate the tempo of life across Pangaea, coordinating migrations, breeding seasons, and plant cycles in a rhythm that echoes across the entire landmass. Finally, imagine witnessing this dynamic interplay. A pterosaur soars along the length of a mighty river, winds carrying it effortlessly for hundreds of kilometers. Dust from distant deserts settles on the banks, nourishing riparian forests where ferns, seed ferns, and early gymnosperms grow densely. Rivers twist and branch across plains, mountains, and valleys, forming a network of life-sustaining channels. Seasonal rains swell these waterways and monsoonal winds herald the coming of wet months, bringing water and nourishment to parched regions. Every gust, every current, every river bend is part of a living system that sustains life, a memory of winds, a pulse of water flowing continuously across the supercontinent. In this Pangaean world, life is not confined by seas or islands. It is guided, nourished, and connected by the invisible hand of the wind and the tangible veins of water. Rivers and winds sculpted the supercontinent's ecology, enabling species to disperse, adapt, and interact on unprecedented scales. They created corridors for migration, avenues for genetic exchange, and pathways for the rise of complex ecosystems. The memory of winds and the pulse of rivers define the supercontinent's story, a tale of life shaped by forces both gentle and relentless, sweeping across thousands of kilometers of landmass and leaving a lasting imprint in the rocks, fossils, and the imagination. Pangaea's rivers and winds were the lifeblood of the supercontinent, silently orchestrating a symphony of ecological and evolutionary processes. They remind us that even in a world without boundaries, subtle forces, the direction of a breeze, the path of a river, can shape life on the grandest scales. The veins of water and the memory of winds are not just geological phenomena. They are the pulse and breath of a world in motion, connecting ecosystems, guiding migrations, and shaping the destiny of species across an Earth that, for a fleeting moment in deep time, was whole. Beneath the surface of Pangaea, where continents kissed and collided, ancient forces slumbered, slow, molten, patient. Forces as old as the Earth itself. They pulsed not in seconds or seasons, but in eons, stirring the molten mantle, cracking stone with the weight of eons, lifting mountains, folding bedrock, and cracking deep gorges into the flesh of the earth. And sometimes, these hidden forces refused silence. They roared. There are moments in the planet's deep memory when fire rose to meet sky, and stones, once content to lie buried, were flung aloft in a fury of ash and lava. On Pangaea, such moments were not isolated. They echoed in chains, volcanic arcs that stretched for thousands of kilometers, birthed where tectonic plates collided like ancient beasts locked in a slow-motion wrestle, forcing the crust to buckle and break. Imagine the sky of a Pangaean day turned suddenly dark, not by cloud but by smoke and ash. Mountains, newly born of pressure, split open and the earth vomited fire. The very atmosphere trembled. Forests bent before the heat and shock waves. Rivers boiled along their edges. And the sun became a memory behind veils of sulfur and soot. These were not ordinary eruptions. They were events that redrew coastlines, that seeded new soils, and that, at times, silenced life itself. Where did this fury begin? Deep below the crust, heat from Earth's molten core churned the mantle in vast, looping currents. These convection currents pushed continents together and tore them apart. When they collided, like the massive crush of Gondwana and Laurasia to form Pangaea, they squeezed stone as one might squeeze clay, raising entire mountain ranges, like the central Pangaean Mountains, and setting the stage for seismic and volcanic drama. Volcanoes formed along these plate boundaries, stretching in volcanic arcs across ancient terrain. Some emerged gradually, oozing basaltic lava that cooled into dark plains. Others exploded violently, releasing plumes that soared miles into the stratosphere. Along the margins of Pangaea, especially where oceanic crust plunged beneath continental plates, volcanic arcs like ancestral echoes of today's Andes or Himalayas shook the land. In these zones, magma found weakness, fault lines, fissures, fractures, and surged upward with purpose. As it rose, it melted surrounding rock, collecting gases like carbon dioxide and sulfur dioxide until the pressure became unbearable. Then, eruption. Not once. Not briefly. Some of these volcanoes remained active for hundreds of thousands of years. But among all the volcanic events during the reign of Pangaea, none compared to one, the great outpouring of fire that formed the Siberian Traps. About 252 million years ago, near the close of the Permian period, in the heart of what is now Siberia, the earth tore open. Not in a single spot, but in a series of massive fissures that bled lava across millions of square kilometers. This was not a mountain-building event. It was a flood, an ocean of molten rock that surged across the land, burying forests, boiling rivers, and changing the chemistry of the very sky. The scale defies imagination. Over 2 million square kilometers were flooded with basalt, an area larger than modern-day Mexico. The eruptions lasted for nearly 1 million years, pulsing with intermittent violence, sending gases high into the atmosphere. Carbon dioxide, methane, sulfur dioxide, each molecule a tiny saboteur in the planet's climate system. Global temperatures spiked. Oceans acidified. Rain turned to acid. The balance of life, already delicate, teetered and fell. This event, driven by volcanoes shaped by mantle heat, ushered in the Permian Triassic extinction, the most catastrophic mass extinction in Earth's history. Over 90% of marine species and 70% of terrestrial species vanished. Coral reefs collapsed. Insects disappeared. Forests turned to deserts. The Earth became, for a time, a quieter, emptier place. And yet, this silence was part of the larger rhythm. From fire came destruction, yes, but also renewal. Volcanoes, though terrifying, are also artists of creation. The ash they cast upon the land becomes fertilizer. The gases they release into the sky shape climate cycles. The land they burn and bury becomes the substrate for new ecosystems. In the wake of the Siberian Traps, as temperatures gradually cooled and life clawed back its place, new species evolved, adapted to the altered world. Over time, grasses crept over cooled basalt. Ferns reclaimed volcanic valleys. Amphibians emerged, then reptiles, then the earliest ancestors of dinosaurs, creatures that would one day rule the Earth for over 150 million years. Even as life endured, volcanoes remained, always watching. Along Pangaea's central ridges, smaller volcanic systems erupted periodically, reshaping local environments, forming lakes and highlands. Gases from these eruptions, especially CO2, acted like a planetary thermostat driving long-term climate changes. At times, greenhouse gases warmed the world. At other times, volcanic ash dimmed sunlight, cooling the globe for millennia. The climate was never static. It breathed with the planet's core. And the rhythm of this breath was dictated by the stones of fate, the volcanoes that, through fire and fury, dictated when species would flourish or fall. Paleontologists have discovered layers of volcanic ash in sedimentary rocks around the world, tied to these ancient eruptions. In South Africa's Karoo Basin, fossil beds show patterns of extinction and recovery that match the timeline of the Siberian Traps. In China's Maishan region, chemical signatures in rock strata record abrupt climate shifts, spikes in carbon and sulfur, indicating massive gaseous emissions. These aren't just rocks. They are records. Each layer a page in Earth's autobiography. They tell us that volcanoes are not simply destructive. They are also chroniclers of destiny. But what exactly made the Siberian Traps so deadly? The answer lies in scale, timing, and location. When lava surged through Siberia's crust, it didn't just pour across the surface. It intruded into coal-rich sedimentary layers, vast ancient deposits of organic carbon. As magma met coal, it triggered combustion underground, releasing not only volcanic gases, but additional CO2 and methane, further fueling the greenhouse effect. This wasn't just a volcanic eruption. It was a geochemical catastrophe. The atmosphere became a cauldron. Global average temperatures rose by 8 to 10 degrees Celsius, pushing ecosystems past their tipping points. Oceans lost their oxygen, leading to widespread marine die-offs. On land, droughts, acid rain, and toxic gases extinguished countless species, all because of fire. Fire that rose from beneath the earth. Fire that remembered. Even now, as we gaze at basalt cliffs in Siberia or examine ash layers in distant rocks, we are looking into the scars of this planetary trauma. The stones of fate still speak if you know how to listen. Elsewhere on Pangaea, volcanic arcs traced the margins of tectonic collision zones. In what would become the Appalachian Mountains, ancient subduction zones birthed long-extinct volcanoes. On the western edge, now buried beneath modern sediments, similar chains erupted as crust crumpled and buckled. Each volcano had its own signature, its own plume of ash and narrative of eruption, but all danced to the same underlying rhythm, the deep, unyielding heat of Earth's mantle. And with each eruption the biosphere adjusted. Some species perished, others adapted. Flora developed fire-resistant traits. Fauna shifted migration patterns. Evolution was not separate from geology, it was shaped by it, cradled in lava, tested by ash. Even human ancestors, millions of years later, would inherit a world sculpted by these volcanic forces. Soils made fertile by ash. Mountains formed by uplift. Climate cycles written in gases long released. The very air we breathe carries echoes of ancient eruptions. The fates of species, the directions of rivers, the patterns of weather, all can trace their lineage to volcanoes that once burned beneath Pangaea. Fire, then, is not simply destructive. It is a sculptor of destiny. It is the heartbeat of Earth, slow and relentless. As you lie in the quiet of night, think of that deep rumble beneath your feet. Not one you can hear or feel, but one that has never stopped. The core turns. The mantle stirs. And the stones remember. The fire that formed continents, that built mountains and broke them, that ended eras and seeded new ones, still breathes within the earth. The volcanoes of Pangaea are long silent, their mouths buried beneath shifting plates. But their legacy surrounds us, in stone, in soil, in sky. And perhaps one day fire will rise again. Not in anger, but in continuation. For Earth is not a finished painting. It is a living canvas, and fire is its brush. Imagine, if you will, standing at the edge of a dense, mist-laden carboniferous forest on the supercontinent of Pangaea, where the air itself seems heavier, richer, almost intoxicating. Oxygen levels in this ancient world hovered around an extraordinary 30%, far higher than the 21% we breathe today, and this abundance of life-giving gas shaped every inch of the environment in ways both magnificent and peculiar. You might feel the soft hum of the wind through towering lycopsid trees and giant ferns, but there is a second, subtler hum, a vibration of life carried in the beat of enormous wings, the scuttle of colossal legs across the damp forest floor, the faint scrape of armored bodies against leaves and bark. Here, in this world of extremes, evolution played a bold and curious hand, sculpting creatures so vast and strange that our modern imagination struggles to contain them. The forests themselves rise like green cathedrals, their fronds and fronds interweaving into a continuous canopy, filtering sunlight into long shafts of golden, hazy light. Beneath, the ground is soft with decaying plant matter, a thick carpet of carbon-rich humus that would one day form the coal seams fueling the distant future. In these humid lowlands, rivers meander sluggishly, carrying tannin-stained waters that wind between enormous root networks and tangled undergrowth. The environment is both lush and perilous, offering shelter and challenge alike. And upon this stage, creatures of staggering size make their daily journey. Consider the dragonflies. In our present day, they glide gracefully over ponds and streams, rarely stretching more than a few inches across. But here, on Pangaea, dragonflies could reach nearly a meter in wingspan, their iridescent wings slicing through humid air, catching the light in glimmers of emerald and bronze. Imagine watching one swoop past, talon-like legs poised, its eyes a mosaic of lenses reflecting the undergrowth below. The high-oxygen atmosphere allowed their respiratory systems to function efficiently despite their enormous body size, a biological luxury unavailable to modern insects. Every beat of those enormous wings creates subtle gusts that rustle ferns, sway saplings, and stir the thick, humid air. They are predators, scavengers, and navigators all at once, tracing invisible lines through a labyrinth of ferns, lycopsids, and towering horsetails. Scientists still debate how exactly these enormous wings and bodies evolved. The precise interplay between oxygen levels, predation pressures, and ecological opportunity remains a tantalizing mystery. And on the ground, the forest floor hosts creatures equally impressive. Millipede-like arthropods, some stretching up to 2 meters in length, move methodically among the wet leaf litter, their countless legs creating a symphony of tiny, synchronized movements. These behemoths, ancestors of modern myriapods, browse upon decomposing vegetation, slowly recycling nutrients through an ecosystem that depends on constant motion and decay. They are armored, yet flexible, and their segmented bodies allow them to navigate the uneven terrain with an elegance belied by their size. You might imagine stepping carefully to avoid being brushed aside by one of these colossal creatures as it seeks shelter or food, a gentle giant among the roots and mosses. The high atmospheric oxygen allowed muscle tissue to maintain endurance across long distances, making movement both sustained and energy efficient, a physiological adaptation that scientists are still trying to fully understand. In the swamps, scorpions the size of modern dogs patrol, their pincers opening and closing with a precision that belies their massive bulk. Their tails, tipped with venomous stingers, curve and flick with awareness of every vibration in the soil. These predators represent an evolutionary experiment, gigantism in a world that permits it. With few aerial predators capable of threatening them, they occupy niches that are now unfathomable, balancing strength and stealth with the delicate, almost hypnotic rhythms of the Carboniferous environment. Fossilized tracks suggest these animals moved in purposeful, deliberate ways, surveying their territories and responding to subtle environmental cues, humidity gradients, decaying plant scents, and the approach of prey. Even aquatic habitats in this era reflect this trend toward gigantism. Freshwater rivers and ponds are inhabited by enormous arthropods and early amphibians, whose elongated limbs and expansive body surfaces benefit from the oxygen-rich waters and air. Giant dragonfly nymphs lurk in shadowed waters, ambushing smaller invertebrates, their eyes scanning every ripple. Early amphibians, sprawling and muscular, emerge onto riverbanks, their skin glistening in filtered sunlight, ready to claim resources both in water and on land. Life in this high-oxygen world is intense, energetic, and surprisingly interconnected. The growth of one species often creates space for another, a cascading evolutionary ripple visible in both form and behavior. Consider, too, the evolutionary oddities: winged insects with patterns reminiscent of abstract art, millipedes whose segments carry specialized appendages, and scorpions exhibiting behaviors unusual for their size and physiology. Each anomaly tells a story of experimentation, of evolutionary what-ifs allowed by the environmental canvas. Scientists still debate whether these adaptations were driven primarily by oxygen levels, predation pressures, or resource availability. Some argue that gigantism was a direct consequence of atmospheric chemistry. Others suggest complex ecological interactions amplified these effects. Whatever the cause, the result is a landscape alive with creatures whose scale and behavior push the boundaries of what we consider possible. The night in these forests, when it falls, is no less spectacular. Shadows of dragonflies pass across the shimmering swamp waters, giant millipedes burrow silently through moist soil, and scorpions pause beneath the canopy, their segmented bodies reflecting moonlight filtered through fern fronds. You can almost hear the faint resonance of wings and legs moving in harmony with the subtle creak of trees and the drip of condensed moisture from the leaves above. Every sound, every movement, is amplified by the scale of the organisms and the density of the environment, creating a symphony of life that is both mesmerizing and hypnotic. Close your eyes and picture this scene: the soft rustle of fern leaves, the distant buzz of enormous wings, the glimmer of armored exoskeletons moving across leaf litter. Let your imagination drift into the slow, deliberate rhythm of Pangaea's Carboniferous world, where life thrived in shapes and sizes unlike anything we know today. Even the smallest details contribute to the majesty of this world. The exoskeletons of giant insects glint in sunlight like polished bronze, veins in their wings trace intricate patterns, and tiny hairs detect the slightest vibrations of passing predators or prey. Millipede segments interlock with mechanical precision, allowing coordinated movement across uneven terrain, while scorpions' pincers grasp with delicate but formidable strength. The air, saturated with oxygen, feels almost tangible, denser, fuller, charged with the possibility of enormous life. High above, dragonflies hunt, scuttling insects flee, and millipedes navigate the undergrowth, each creature existing within a complex network of interactions. Predation, reproduction, and survival are all influenced by the atmospheric richness, which enables metabolic processes that allow for sustained activity, enormous size, and evolutionary exploration. Patterns of behavior emerge: nocturnal and diurnal rhythms, migratory movements across swamp networks, seasonal bursts of activity following rainfall. These ancient cycles, fossilized in trace evidence and preserved in coal and stone, speak to an ecosystem both delicate and robust, resilient and ephemeral. Yet there is also fragility. While oxygen permitted gigantism, it also made organisms susceptible to fire, as dense vegetation combined with rich air fueled sudden, intense blazes that swept across lowlands. Fossilized charcoal layers attest to recurring fires that both destroyed and renewed landscapes, shaping species evolution through cycles of devastation and regrowth. Predators adapted, prey adapted, and the forest itself adjusted in response, creating a dynamic interplay between fire, oxygen, and life. In your mind, step closer and imagine a dragonfly, its massive wings catching golden light, skimming over the river's surface. A millipede inches along a decomposing log nearby, its thousands of legs orchestrating movement like a living metronome. A scorpion pauses in the mud, sensing vibrations from a distant predator. Each organism is a marvel, a testament to the interplay of environment, physiology, and evolutionary chance. High oxygen levels, immense swamps, and endless ferns converge to allow creatures of improbable size to thrive, to leave a mark on the fossil record that we study today with awe and curiosity. So as you breathe slowly, letting the vision of Pangaea's Carboniferous forests fill your mind, consider the lessons of this high-oxygen world. That environment shapes evolution, that extremes allow creativity in biology, that life can expand in ways we can scarcely imagine, and that our modern world is but a fraction of the possibilities once realized on Earth. The dragonflies, the millipedes, the scorpions, all echoes of a world where the very air allowed ambition, where survival was measured in wing beats and legged marches, and where evolution's hand was both bold and whimsical. Scientists continue to investigate these marvels, uncovering new fossils, refining theories, and marveling at a past that seems almost dreamlike in its strangeness. Let your mind linger here, among the massive ferns and the shimmering rivers, following the great dragonflies as they wheel through filtered sunlight, the millipedes tracing elegant patterns through the undergrowth, the scorpions testing the soil and roots. Every detail of this lost world is a thread in a tapestry of life, a reminder that Earth's history is vast, imaginative, and endlessly surprising. The creatures of Pangaea's high oxygen age are more than curiosities. They are an invitation to see life as it once was, to feel the pulse of evolution in a world at once alien and beautiful, and to drift into a contemplative, dreamlike state where imagination meets science. Step softly into the shadows of deep time, and allow your imagination to drift back nearly 252 million years, to the waning days of the Permian period. Pangaea still dominates the globe, stretching like an immense, unbroken ribbon of land across equatorial, temperate, and polar zones. Forests, deserts, rivers, and swamps sprawl uninterrupted, sculpted over tens of millions of years by tectonic dance, atmospheric rhythms, and the interplay of life itself. Yet beneath this seemingly eternal landscape, a storm is gathering, a slow, simmering force that will leave no corner of the supercontinent untouched, no species unchallenged. This is the dawn of the Great Dying, the Permian Triassic extinction event, the most devastating mass extinction in Earth's history. It is a time when life, as it has existed for hundreds of millions of years, faces annihilation on a planetary scale. The origins of this calamity lie deep beneath the Siberian landscape, in what is now called the Siberian Traps, a vast region of volcanic rock covering millions of square kilometers. Here, molten rock rose relentlessly through the crust, erupting in massive flood basalts that would cover the land in rivers of lava and clouds of ash. These eruptions were not occasional or isolated. They were continuous and vast, spanning hundreds of thousands of years, with pulses of volcanic activity painting the skies with smoke, dust, and heat. The immensity of these eruptions is hard to comprehend. Imagine the relentless roar of fire and stone, miles-long sheets of lava oozing across ancient valleys and plains, while volcanic gases pour skyward, shrouding the supercontinent in haze. Carbon dioxide and sulfur compounds, released in mind-boggling quantities, flood the atmosphere, creating a greenhouse effect that drives temperatures to extreme highs. Sulfuric acid aerosols, meanwhile, dim sunlight and acidify rainfall, leaving soils and shallow waters hostile to life. As these gases infiltrate the air and oceans, the environment begins to unravel. Forests, once dense and thriving, succumb to scorching heat, drought, and acid precipitation. In shallow seas, nutrient cycles collapse, and marine ecosystems become increasingly unstable. Oceanic anoxia, zones of depleted oxygen, spread across the Panthalassa, suffocating marine animals. Coral-like organisms, brachiopods, and trilobite descendants struggle to survive. Vast reefs crumble. On land, insects, amphibians, and early reptiles face heat stress, dehydration, and disrupted habitats. The interconnectedness of ecosystems, which once promoted thriving diversity across the supercontinent, now amplifies vulnerability. The extinction of one group ripples through food webs, destabilizing entire communities. Fossil records offer chilling testimony. Layers of rock from this period reveal sudden declines in species abundance and diversity. Fossilized forests show charcoal deposits, evidence of wildfire after wildfire fueled by both high oxygen levels and ignitable vegetation. Marine sediments display extinction markers. Ammonoids and foraminifera vanish, leaving empty shells and gaps in the stratigraphy. Even the burrows of soil-dwelling creatures become sparse or disappear altogether, suggesting that life, both above and below the ground, is under siege. Paleontologists note that nearly 90 to 96% of marine species and 70% of terrestrial vertebrates vanished during this period, a magnitude of loss that dwarfs all other mass extinctions before or since. The mechanism of this cataclysm is complex. a confluence of volcanic activity, atmospheric change, and ecological vulnerability. Massive lava flows release carbon dioxide, triggering global warming that raises temperatures by perhaps 6 to 10 degrees Celsius, while sulfur aerosols provoke acid rain. Methane, trapped in permafrost and oceanic clathrates, may have erupted in sudden bursts, exacerbating greenhouse effects. Ocean acidification weakens the shells and skeletons of marine animals, while oxygen depletion suffocates those reliant on aerobic respiration. On land, drought and heat stress reduce plant productivity, leading to cascading food shortages for herbivores and in turn carnivores. Ecosystems, finely balanced for millions of years, collapse under multiple simultaneous pressures. Remarkably, the extinction is not uniform. It varies by latitude, habitat, and ecological specialization. Polar forests, somewhat insulated from the immediate warming, endure slightly longer, while low-latitude deserts and equatorial swamps suffer first. Species that can burrow, migrate, or tolerate extreme heat may survive longer, but survival is precarious and temporary. The fossil record preserves ghost lineages, creatures that endure only briefly before succumbing. This patchwork of survival and extinction offers clues to the resilience and fragility of life. Adaptation is necessary, yet sometimes insufficient against overwhelming environmental change. Marine life, particularly, bears the brunt of the great dying. Reef-building organisms, which have flourished for hundreds of millions of years, collapse. Sponges, brachiopods, and early mollusks vanish from many sedimentary layers. The disappearance of these keystone species disrupts entire marine food webs. Predatory fish and early reptiles face starvation as their prey declines, while planktonic organisms struggle in warming, oxygen-depleted waters. Evidence of euxinic conditions, water rich in hydrogen sulfide, emerges in geochemical markers, suggesting the oceans themselves become toxic. Paleontologists reading these rocks can almost sense the suffocating waters, the absence of sunlight, the quieting of ecosystems once filled with motion and color. On land, the story is equally stark. Plants face desiccation, wildfires rage across forests, and vast stretches of Pangaea's interior transform into barren landscapes. Reptiles, amphibians, and insects, once thriving in diverse niches, are pushed to their limits. Fossil evidence indicates abrupt shifts in flora, with gymnosperms and seed ferns surviving better than spore-bearing plants in some regions. This selective survival reshapes terrestrial ecosystems for the Triassic, paving the way for new lineages that will dominate the next geological era. The Siberian Traps eruptions also leave a chemical fingerprint in rocks. Mercury anomalies, high levels of carbon isotopes, and layers rich in nickel and platinum group elements. These geochemical signatures allow modern scientists to trace the sequence and timing of the events with remarkable precision. Each lava flow, each volcanic pulse, represents not only a physical event but a profound ecological shock, leaving an indelible mark on the geologic record. The Great Dying, while catastrophic, also sets the stage for renewal. Following the extinction, niches are left vacant, evolutionary pathways are opened, and new lineages emerge to inhabit spaces once crowded with life. The Triassic sees the rise of early dinosaurs, mammals, and modern plant groups, all beneficiaries of the ecological reset imposed by the Permian-Triassic extinction. Fossils reveal a slow but steady recolonization, a testament to life's persistence despite cataclysm. Yet the memory of the Great Dying lingers, embedded in the stratigraphy, in isotopic anomalies, and in the evolutionary trajectories of surviving lineages. Consider the emotional weight of this epoch. Standing metaphorically at the boundary between the Permian and Triassic, one witnesses both annihilation and hope. Life endures, but it is unrecognizable compared to what came before. Ecosystems are fragmented, species composition transformed, and the ecological equilibrium of Pangaea is forever altered. It is a stark reminder of Earth's vulnerability, of the immense power of geologic and atmospheric forces, and of the intricate interdependence of life and environment. As you imagine this world, picture rivers drying, forests cracking under heat, volcanic plumes blotting out sunlight. Hear the silence that follows the storms, punctuated only by the occasional rustle of a surviving organism. Visualize shallow seas turning toxic, reefs crumbling, and the final gasps of species that once thrived in abundance. The Great Dying is both terrifying and instructive, a planetary event that underscores the fragility and resilience of life, and the profound influence of Earth's geologic processes on biology. In reflection, the Permian Triassic extinction teaches us about scale, interconnectedness, and consequence. It reminds us that Earth is not static, that continents drift, volcanism reshapes the atmosphere, and life responds in unpredictable ways. Fossils and chemical signatures in rocks serve as clues, guiding scientists through a narrative of catastrophe and recovery. And as we meditate on this ancient apocalypse, we gain not only insight into the past but perspective on the present. The planet has faced extreme change before, and its history is a tapestry of survival, adaptation, and the relentless forces of nature. Let your mind linger in this moment of transition. Visualize the thick volcanic haze, the air heavy with carbon, the oceans sluggish and toxic. Picture the survivors, small, resilient, adaptable, emerging from chaos to lay the foundations for a new era. The Great Dying is the ultimate testament to Earth's power and life's persistence. A profound lesson written in stone, lava, and fossilized remains, echoing across 252 million years to reach us today. Long after the searing heat of volcanoes had faded and the acrid smoke of the Siberian traps had begun to settle into a faint memory, a remarkable hush fell over Pangaea. The once thrumming forests and teeming riverbanks lay eerily quiet, a vast silence that stretched from the equatorial wetlands to the icy reaches of the southern Gondwanan expanse. Yet within this stillness, life persisted. It was not the grand spectacle of sprawling giant insects or enormous amphibians that now dominated the land. Instead, it was the subtle, resilient, and often overlooked creatures, the ones capable of enduring hardship, of adapting against the odds, that began to reclaim the stage. Tonight, let us walk carefully along the footprints of survival, tracing the story of those tenacious species who emerged from the shadow of the Great Dying, and imagine how they began to rewrite Earth's biological narrative. The extinction event that had swept across the planet, what scientists call the Permian Triassic extinction or the Great Dying, had eradicated more than 90% of marine species and over 70% of terrestrial vertebrates. Entire ecosystems collapsed. Forests were reduced to skeletal remnants, rivers ran murky with ash and sediment, and the once complex web of life that stretched across continents now seemed fragile and fragile alone. Yet in pockets of refuge, life clung to persistence. Tiny reptiles scuttled beneath fallen logs. Minute amphibians found shelter within residual swamps and ephemeral ponds. Hardy plants, adapted to endure drought and scorching heat, held on in scattered oases along drying riverbeds. Even within this seeming desolation, the seeds of renewal quietly stirred. Among the survivors were small synapsids, often referred to as the mammal-like reptiles, creatures whose subtle forms belied their extraordinary evolutionary potential. These animals had weathered the lethal combination of atmospheric toxicity, extreme global warming, and oceanic anoxia. Their modest size became an advantage, allowing them to seek shelter, conserve energy, and exploit resources that larger animals could no longer access. Over the following millennia, their lineage would gradually evolve more complex dentition, more efficient locomotion, and physiological traits that increasingly resembled those of the mammals we know today. Each subtle adaptation was a step along a path forged in the crucible of extinction, each incremental change a chapter in the emerging story of terrestrial life. Meanwhile, the survivors among early reptiles and amphibians exploited ecological niches left vacant by vanished species. Arboreal creatures crept along fragmented canopies, while burrowers tunneled beneath scorched earth, stabilizing soils and creating microhabitats that nurtured both plant and animal life. These survivors were the quiet engineers of a reshaped biosphere, laying foundations upon which new ecosystems could flourish. Small herbivorous reptiles began dispersing seeds, contributing to the slow regeneration of forests. Insects, though diminished in diversity and abundance, remained active agents in pollination and nutrient cycling, helping to knit together a recovering web of life. Plants, too, demonstrated remarkable resilience. Xerophytic species, capable of surviving prolonged drought and intense solar radiation, dominated the devastated plains. Their deep root systems held eroding soil in place, preventing further ecological collapse, while pioneer species gradually recolonized disturbed terrains. In wetter equatorial zones, ferns, horsetails, and cycads re-emerged, forming pockets of dense vegetation that served as lifelines for returning herbivores and their predators. Slowly, these nascent forests spread, shading the once barren land and producing oxygen to rebuild the atmosphere weakened by volcanic emissions. Across the expanse of Pangaea, these surviving species did not remain isolated. The absence of formidable competitors and the vast, uninterrupted landmass allowed for unprecedented dispersal. A synapsid might traverse hundreds of kilometers over geological timescales, spreading genetic material across vast stretches of the supercontinent. Amphibians and reptiles found new rivers and floodplains to inhabit, gradually reoccupying territories that had once been dominated by larger, now extinct species. Insects followed, pollinating and feeding, perpetuating cycles that had been briefly interrupted. This was the slow, quiet resurgence of life, a testament to adaptability and tenacity. Fossil evidence from this period underscores the remarkable homogeneity of some surviving species across what would later become separate continents. The same genera found in now distant lands hint at an interconnected world in which survivors roamed freely across Pangaea's continuous terrain. It was a world with few barriers, where evolution proceeded not in isolated pockets but across vast expanses, facilitating both genetic exchange and the emergence of novel traits. Scientists still debate the exact mechanisms that allowed these few species to persist while the vast majority perished, but the fossils speak clearly. Survival favored small size, adaptability, and behaviors that mitigated exposure to the most extreme environmental fluctuations. Amid these survivors, evolutionary experimentation flourished. Synapsids developed increasingly differentiated teeth, suited to a variety of diets, from insectivorous nibbling to herbivorous grinding. Limb morphology shifted, accommodating faster movement and better balance. Burrowing behavior became more sophisticated, allowing individuals to escape both predators and climatic extremes. This quiet ingenuity laid the groundwork for the eventual rise of mammals, whose ancestors navigated these harsh landscapes with ingenuity and persistence. Predatory species that endured, often smaller and more opportunistic than their predecessors, capitalized on the void left by extinct apex predators. They demonstrated remarkable flexibility, shifting diets according to availability, moving between habitats and avoiding competition wherever possible. Insects, arachnids, and other invertebrates, taking advantage of reduced predation pressure, diversified in form and behavior. Some developed elongated limbs for climbing recovering vegetation, others adapted to new water sources, and still others evolved defensive strategies to contend with the survivors' predation. In parallel, the interplay between surviving flora and fauna began to shape the physical environment. As plant communities recovered, soil quality improved, humidity increased in localized areas, and microclimates began to stabilize. Rivers and floodplains slowly reasserted their flow, guided in part by vegetative growth that mitigated erosion and sediment movement. Ancient wind patterns, once dominated by broad desert expanses, interacted with these recovering ecosystems, carrying spores, seeds, and dust that helped recolonize barren stretches. Life itself became a sculptor of the supercontinent, remolding the environment to favor survival and further diversification. This period also saw the early stages of ecological experimentation that would define the Mesozoic. Small herbivores evolved defensive traits such as hardened skin, spiny appendages, or burrowing behaviors to evade predation. Predators, in turn, refined strategies for hunting in these emerging ecosystems. Symbiotic relationships began to emerge, and complex food webs slowly reformed. The survivors of the Great Dying were not merely relics. They were pioneers in an ecological renaissance, crafting a world where life could thrive once again. It is fascinating to consider that each small creature surviving this mass extinction carried within it the potential for evolutionary innovation. Every tiny synapsid, each resilient plant, and every adaptable amphibian contributed threads to a tapestry of life that would, in the coming millions of years, give rise to the diverse ecosystems we now study in the fossil record. The Great Dying had pruned the tree of life brutally, but it had also set the stage for new growth, for experimentation, and for the rise of lineages that would shape the future of Earth's biodiversity. As we imagine the supercontinent recovering, let us envision the slow, meticulous expansion of life across Pangaea's scarred landscapes. Consider the synapsids scurrying beneath the shadows of resurgent ferns, the small reptiles navigating newly formed rivers, the plants stretching their roots into sun-scorched soil, and insects once again filling the air with their delicate hum. It is a tableau of resilience, of creativity born from necessity, a testament to the incredible capacity of life to endure, adapt, and flourish. And in the stillness of this moment, as Pangaea's survivors charted their new scripts, we witnessed the subtle origins of future giants. The dinosaurs, the mammals, the birds, the flowering plants, all owe a debt to these modest survivors who clung to life when the world seemed to have abandoned them. In their quiet persistence, they crafted a biological blueprint that would echo across eons, shaping the evolutionary pathways that continue to influence Earth to this day. This is the story of survival not as a dramatic clash of titans, but as a quiet, pervasive triumph of adaptability and resilience. Every footprint, every burrow, every seed, and every delicate breath contributed to the intricate renewal of Pangaea. Life was not defeated. It had paused, reflected, and then emerged with renewed ingenuity, weaving the foundations for an entirely new chapter in Earth's history. And as we close our eyes to imagine these ancient landscapes, we can almost hear the gentle rustle of leaves in recovering forests, the soft scuttle of small reptiles across sun-warmed rocks, and the distant call of creatures who would go on to inherit the world. Long before the first human eyes would ever see mountains or oceans, long before the whisper of wind or the murmur of rivers, the earth itself was in motion beneath the surface. Pangaea, the mighty supercontinent that had once held nearly all of the world's landmass in a single continuous embrace, was no longer an unbroken expanse. Deep within the mantle, where heat and pressure brewed in unrelenting intensity, forces both subtle and immense were gathering. The very heart of the supercontinent, once seemingly eternal and immovable, began to betray a tension that would eventually split the land apart. Tonight, we turn our attention downward, into the molten depths and along the earliest fractures, to witness the slow unraveling of a world that had appeared everlasting. Beneath Pangaea's seemingly solid crust, the mantle pulsed with heat. Convection currents, slow but persistent, carried molten rock in a cyclical rhythm, rising in some regions and sinking in others, like the steady breath of a colossal organism. These currents exerted pressure on the overlying lithosphere, the rigid outer shell of the Earth. Over millions of years, the strain accumulated along zones of weakness where plates had been welded together, places where the crust was less resilient. The forces that had once held Pangaea intact now worked quietly in the opposite direction. The same mechanisms that had brought continents together, subduction, collisional folding, the flow of the mantle beneath, were preparing the supercontinent's eventual undoing. The earliest signs of tension were subtle. Rocks deep underground began to stretch, minute fissures forming along long linear belts. These proto-fractures were narrow, almost imperceptible at first, but they represented the initial whispers of disintegration. As the mantle pushed upward, heat softened the base of the crust, creating zones where the lithosphere was less able to resist the stress imposed by the planet's inner currents. In places where the crust was thick and resistant, the pressure was absorbed slowly, but in thinner regions the forces began to manifest as tension, a gentle pulling apart that would later widen into cracks and valleys. Over time, these fissures grew into more recognizable forms. Geologists today call them rift valleys, long narrow depressions formed where the crust stretches and thins under tectonic forces. In Pangaea, rifts first appeared inland, away from the stabilizing influence of the surrounding oceans. These nascent valleys were the earliest indicators of continental fragmentation, the initial outlines of what would eventually become separate landmasses. Magma from the mantle occasionally intruded along these rift zones, creating swells of molten rock that, as they cooled, hardened into ridges and small volcanic features. These intrusions further weakened the crust, providing additional pathways for eventual separation. The process was painstakingly slow. For millions of years, the land experienced tension that was imperceptible on a human timescale but monumental in geological terms. Along the rifts, the lithosphere thinned, stretching like taffy under immense pressure. Small earthquakes shook the nascent valleys, releasing minor amounts of energy, and volcanic vents occasionally opened, releasing gases and lava that reshaped the local topography. The mantle below continued its silent work, pushing upward and outward, while the crust above strained to maintain cohesion. It was a delicate balance, a dance between resistance and inevitability. As these rift valleys lengthened, the effects on Pangaea's surface became increasingly evident. River systems that had once flowed unobstructed across the supercontinent now encountered depressions that altered their courses. Lakes began to form in the subsiding valleys, collecting sediment eroded from surrounding uplands. Vegetation adapted, colonizing new low-lying wetlands, while some species were forced to migrate along the slowly shifting land. In essence, life itself began to respond to the first cracks beneath the surface, anticipating changes that would unfold over tens of millions of years. The most dramatic early rifts formed along zones of pre-existing structural weakness, often corresponding to ancient sutures from previous collisions between landmasses. These zones, where plates had once welded together, were now the first to yield under the combined stress of mantle heat and lithospheric stretching. Linear depressions, sometimes hundreds of kilometers long, traced the outlines of Pangaea's eventual fragmentation. Along these rifts, basaltic lava flows emerged, creating elongated volcanic ridges. These volcanic features, though modest compared to later events such as the Siberian Traps eruptions, were nevertheless significant agents of change, subtly lifting and fracturing the surrounding crust. Beneath these rifts, mantle plumes, columns of exceptionally hot rock rising from deep within the earth, further exacerbated the tension. Their buoyant force acted like a wedge, pushing upward against the overlying lithosphere, thinning it and facilitating the growth of fissures. Where these plumes intersected with rift valleys, magma welled to the surface, creating local volcanism that injected heat and material into the crust. Over time, repeated intrusion and surface eruptions compounded the weakening of the supercontinent, gradually preparing it for the eventual opening of new ocean basins. The ecological consequences of these geological processes, though subtle at first, were profound. As the crust stretched and valleys formed, drainage patterns shifted. Sediment began to accumulate in new lowlands, altering soil composition and creating microhabitats that supported pioneering plant species. Forests and wetlands slowly adapted to the evolving landscape, while animals responded to the creation of depressions, new water bodies, and modified terrain. Even the high central deserts of Pangaea felt the impact, as rifts subtly redirected wind patterns, influencing evaporation and precipitation cycles across vast distances. The Earth's interior movements had, in essence, begun reshaping the very conditions that supported life on the surface. Across the supercontinent, these processes were not uniform. Some regions resisted deformation longer, while others yielded more readily. In the equatorial zones, where the crust was already under thermal stress from intense solar heating and mantle dynamics, rifts appeared more rapidly. In higher latitudes, the thickened lithosphere delayed the onset of fracturing. Yet everywhere, the inexorable forces from below were at work, reminding us that Pangaea, despite its immense scale and apparent solidity, was never permanent. Its cohesion had been temporary, a fleeting alignment in the slow, continuous evolution of Earth's tectonic puzzle. As the rifts matured, they began to interact. Fault lines propagated outward, intersecting and sometimes branching, creating networks of weakness that would ultimately guide the trajectories of nascent continental fragments. The alignment of these cracks often dictated the orientation of future oceans, the positioning of mountain ranges, and the pathways along which rivers would flow. It is in this stage that the initial scars of the future Atlantic, Indian, and other oceans began to form, almost imperceptibly at first, as linear depressions deepened and widened over millions of years. Within these early rift zones, volcanism and seismic activity continued, sometimes catastrophically. Localized eruptions spewed lava and ash, altering the chemical composition of soils and influencing microclimates. Earthquakes adjusted the topography, creating fault-block mountains and isolated basins. These events, while disruptive to life, also created new ecological opportunities, allowing resilient species to exploit niches and to disperse along newly forming corridors. In this way, tectonics and biology were intricately linked. The physical tearing of Pangaea beneath the surface directly influenced the evolutionary paths of the organisms that had survived previous mass extinctions. The full unfolding of Pangaea's separation would take tens of millions of years, but the first cracks, the rift valleys, represent the earliest steps toward a transformed Earth. They were the whispered hints of continental drift, the subtle beginnings of new ocean basins, and the initial gestures of a planet reshaping itself. While the surface of the land might have appeared stable to a casual observer, the forces beneath were relentless, working quietly yet inexorably to pull apart the very fabric of the supercontinent. In tracing these processes, we see a remarkable story of cause and effect. Mantle heat and convective currents impose pressure, crustal weakness gives way, fissures form, rift valleys elongate, and volcanic activity amplifies the fracturing. Life responds, adapting to shifting landscapes and changing climates. Over eons, these small beginnings set the stage for the dramatic breakup of Pangaea, the formation of the Atlantic and Indian Oceans, and the continental arrangements that we recognize today. The cracks beneath our feet, though invisible on a human scale, were the first chapters of a tectonic drama that continues to unfold. Each rift valley, each fault line, each plume of rising magma, was a reminder that the Earth's surface is alive and ever-changing. Pangaea's unity, once so seemingly permanent, was always conditional, always subject to the deep, inexorable forces of the mantle. In observing these earliest signs of disintegration, we are witnessing a planetary process that has been repeating for billions of years. Continents come together, stay together for a time, and then tear themselves apart, creating the dynamic, ever-shifting world we inhabit today. Even as Pangaea began its slow unraveling, the planet beneath it remained a reservoir of energy and potential. Magma, molten and mobile, carved paths through the lithosphere, forming embryonic mid-ocean ridges that would one day separate the landmasses entirely. Faults lengthened and widened, rivers began to respond to the altered topography, and ecosystems adjusted in real time to these imperceptibly slow but ultimately monumental changes. Every small fissure, every narrow rift, was a precursor to a world in motion, a world that would no longer be unified under a single supercontinent but would evolve into the mosaic of continents and oceans we now recognize. And so, in the silence of the rift valleys, we hear the first murmurs of continental drift. The Earth, in its deep, patient and persistent way, continues its eternal work, stretching, fracturing, and renewing. The cracks growing beneath Pangaea are the earliest echoes of a dynamic planet, and through them, we glimpse the relentless, magnificent processes that shape every mountain, valley, and ocean basin we see today. Long before humanity would ever name continents or chart the seas, Earth was already composing its next great transformation. Pangaea, once a vast, unbroken expanse of land, was fracturing, and with each widening rift came the slow but inevitable intrusion of water. The planet, patient and persistent, began to exhale in liquid form, as the first breaths of what would become the Atlantic and Indian Oceans seeped into the spaces left by rifting. These waters, subtle at first, transformed the landscape in ways that would ripple through millions of years, shaping coastlines, climates, and the evolution of life itself. Beneath the surface, the tectonic machinery continued its relentless work. Mantle plumes and convection currents pressed upward, forcing the lithosphere to stretch, thin, and crack. Rift valleys lengthened and deepened, some reaching thousands of kilometers. As the crust thinned, it lost the ability to fully resist the persistent pull of the Earth's interior. When the first depressions became deep enough, seawater from Pangaea, the global ocean that had surrounded Pangaea, began to infiltrate these narrow valleys. The land, once unified under a single continental mantle, began to yield, and for the first time in tens of millions of years, water reclaimed territory from the terrestrial expanse. The earliest sea incursions were tentative. Salt water crept into depressions, flooding low-lying areas along the rift margins. These embryonic seas were narrow and elongated, confined to the linear pathways carved by tectonics. Along these nascent shorelines, sediments began to settle, creating environments that would support new forms of life. Microbial mats flourished in shallow waters, providing the first aquatic niches in these emerging seaways. Plant matter from adjacent landmasses accumulated, forming early detrital layers that would eventually fossilize, leaving behind a record of these critical transitions. In the future location of the Atlantic Ocean, the rift stretching between what is now North America and Africa became the most significant corridor for seawater intrusion. Over millions of years, the fissure deepened and widened, forming a narrow, elongated inlet that marked the earliest stages of ocean formation. This nascent Atlantic was unlike any previous oceanic body. Its waters, constrained within the rift, were relatively shallow, but their presence had profound geological and ecological consequences. Erosion patterns along the rift edges changed as currents carried sediments away from the land, depositing them into the newly forming basins. Coastal ecosystems began to emerge, including tidal flats and salt-tolerant vegetation zones that would set the stage for future biodiversity. Simultaneously, in the southern hemisphere, the regions destined to become India, Australia, and Antarctica slowly began their departure from the stable interior of Pangaea. Here, rifts extended along the eastern margins of Gondwana, creating gaps through which seawater started to advance. These areas, initially narrow and fragmented, would eventually give rise to the Indian Ocean. The continental fragments, buoyed by mantle dynamics and the reduction in lithospheric thickness, drifted gradually, their motion slow yet inexorable. Between these separating land masses, shallow seas expanded, connecting with Panthalassa and bringing the first marine currents into the emerging gaps. The interplay between tectonics and hydrology was intricate. As rift valleys widened, the intrusion of seawater exerted pressure back onto the crust. Hydrostatic forces accentuated existing fractures, aiding the progressive separation of continental blocks. Meanwhile, sedimentation within the nascent seas created localized resistance, as sands, silts, and organic material altered the gradients of the channels and influenced water flow patterns. Currents began to carve submarine canyons along the rift margins, establishing the preliminary contours of ocean basins that would evolve over tens of millions of years into fully fledged oceans. Life, ever resilient, responded to these changes. Coastal and nearshore environments became hubs of ecological experimentation. Shallow, saline waters supported early invertebrate communities, while the edges of land masses retained pockets of terrestrial life. Plants colonized the new shorelines, forming mangrove-like assemblages and pioneering salt-tolerant species. Animals adapted as well, with some early amphibians exploiting the transition zones between land and water. The very act of ocean formation created opportunities for diversification, as previously terrestrial species ventured into brackish habitats and early marine organisms expanded into newly available niches. In the emerging Atlantic, the rift between North America and Africa was punctuated by volcanic activity. Basaltic flows erupted along the thinning lithosphere, contributing to the elevation of new landforms and the deposition of volcanic sediments into the expanding water channels. This volcanism, coupled with continuous tectonic stretching, caused repeated cycles of subsidence and uplift, shaping the contours of the earliest ocean basin. These processes, though gradual, laid the foundation for the mid-Atlantic ridge system that would later define the heart of the modern Atlantic Ocean. Far to the south, as India and Australia drifted away from Antarctica, the early Indian Ocean began to form through similar mechanisms. Rifts propagated along the margins of the separating land masses, creating elongated depressions that filled with seawater. Currents established themselves between the fragments, facilitating sediment transport and early marine connectivity. These waterways would become crucial corridors for the dispersion of marine species, linking previously isolated ecosystems and setting the stage for future evolutionary radiations. The initial intrusion of seawater also affected climate. The presence of narrow seas along rift valleys altered wind patterns and evaporation rates, influencing precipitation on adjacent land. Monsoonal systems began to develop in response to these nascent oceans, creating seasonal patterns of rainfall that differed significantly from the dry interiors of Pangaea. Coastal regions became more humid, supporting lush vegetation and wetlands, while inland deserts remained harsh and arid. This climatic differentiation would grow more pronounced as the oceans expanded and continental separation progressed. Meanwhile, the ocean floor itself began to record the tectonic drama. Basaltic crust formed along the spreading centers, solidifying into the first mid-ocean ridges. hydrothermal systems emerged, providing heat and chemical nutrients to nascent marine communities. These ridges were the skeletal framework around which the future ocean basins would develop. Sediments accumulated along the edges, and the gradual sinking of rift valleys created deeper channels, laying down the physical architecture for the eventual Atlantic and Indian Oceans. The process of ocean formation was inherently dynamic. Sea level fluctuations, driven by climatic changes and the thermal expansion of water, alternately inundated and exposed coastal areas. Tides, influenced by the positions of continents and the moon, began to interact with the young seas, carving tidal channels and estuaries. The interplay of tectonics, hydrology, and life created feedback loops. As water eroded land, it created more space for expansion, and as land subsided, it allowed water to penetrate further. This feedback accelerated the establishment of permanent ocean basins, slowly transforming the face of the planet. As the Atlantic and Indian Oceans continued to form, the continental fragments drifted ever further apart. North America moved westward, Africa eastward, and in the southern hemisphere, India, Australia, and Antarctica diverged along complex trajectories dictated by underlying mantle dynamics. Each movement widened the rifts, allowing seawater to penetrate further inland and deepening the nascent basins. The gradual enlargement of these waterways transformed Pangaea from a single, contiguous landmass into a mosaic of continents separated by emerging oceans. Sedimentation in the young oceans recorded the story of this transformation. Sands, silts, and volcanic ash accumulated along the margins, creating layered deposits that preserved evidence of fluctuating water levels, climate variations, and early marine life. Fossilized remains of organisms found within these sediments provide a window into the earliest ecosystems of the Atlantic and Indian Oceans. Invertebrates, algae, and microbial mats thrived in these environments, establishing foundational food webs that would sustain marine life for millions of years to come. The intrusion of seawater into the rift valleys also had chemical consequences. Salinity levels, temperature gradients, and nutrient availability fluctuated, influencing the composition of early oceanic communities. Upwelling along the rift edges brought nutrients from deeper waters to the surface, supporting primary productivity and encouraging the colonization of diverse species. Over time, these physical and chemical dynamics established the conditions necessary for the oceans to develop into complex, life-supporting systems. Even as the water claimed more territory, Pangaea's interior remained relatively stable, retaining vast deserts, mountain ranges, and river systems. These terrestrial landscapes provided a stark contrast to the emerging seas along the rifts. Rivers draining into the new oceans carried sediments and organic matter, linking terrestrial and marine ecosystems in an intricate network of nutrient exchange. The fragmentation of Pangaea, though gradual, created a more complex, heterogeneous planet, where land and water interacted dynamically, and life adapted to an increasingly diverse set of environments. The first breaths of the Atlantic and Indian Oceans were therefore more than a geological event. They were the opening lines of a new planetary chapter. The intrusion of water into rift valleys marked the beginning of continental dispersal, the reorganization of ocean currents, and the establishment of ecological corridors connecting previously isolated regions. These early oceans would grow, merge, and reshape Earth's surface, influencing climate, biodiversity, and the evolutionary trajectory of life itself. In witnessing this transformation, we see the profound interplay between Earth's internal forces and its surface environments. Mantle dynamics push the crust apart, creating rifts that water fills. Tides, currents, and sedimentation sculpt the emerging basins. Life adapts to the changing landscapes and seaways. The formation of the Atlantic and Indian Oceans is a testament to the patient, persistent creativity of planetary processes, and to the capacity of the Earth to renew and reshape itself across deep time. The breath of new oceans, tentative at first, would grow stronger with time. Narrow inlets would expand into broad seas, shallow channels would deepen into ocean basins, and the supercontinent would fragment into the mosaic of continents we recognize today. This process, unfolding over tens of millions of years, represents a profound transition in Earth's history, a moment when water reclaimed land, reshaped the climate, and opened pathways for life to explore a dramatically transformed world. Even as Pangaea continued to fracture, as rifts widened and seas expanded, the story of Earth's oceans had only just begun. The Atlantic and Indian Oceans, born in the quiet intrusion of water into deep fissures, would come to dominate global climate patterns, marine biodiversity, and the movement of continents for hundreds of millions of years. These first breaths of the oceans were both the end of Pangaea's unity and the beginning of a dynamic new chapter, one in which water and land would engage in a continuous, ever-changing dance that shapes the planet to this very day. In the shadowed corridors of Earth's deep past, long before humans ever walked its lands, the stage was quietly being set for a new kind of dominance. As Pangaea endured its final acts of unity and began to fracture, early reptiles, the heirs of the great dying, were experimenting with form, function, and survival strategies in ways that would culminate in one of the most extraordinary evolutionary experiments the planet had ever witnessed. Among these pioneering lineages, some evolved into creatures that would come to define an entire era, the first true dinosaurs. Their story is one of emergence, adaptation, and expansion, intricately bound to the restless motions of the planet itself. During the waning days of Pangaea's cohesion, the terrestrial landscape was vast, continuous, and uninterrupted by modern oceans. The supercontinent offered immense expanses of diverse habitats, arid deserts stretching thousands of kilometers inland, lush tropical belts along the equator, temperate forests in mid-latitudes, and polar woodlands fringed by ice. Early reptiles exploited this abundance, experimenting with bipedal locomotion, elongated limbs, and new feeding strategies. Some of these lineages developed traits that would hallmark the earliest dinosaurs: upright postures, efficient locomotion, and skeletal adaptations that allowed for greater mobility and endurance. In these open expanses, evolutionary pressures favored agility and adaptability, setting the foundation for the rise of a group that would dominate terrestrial ecosystems for over 100 million years. The timing of dinosaur emergence is tightly entwined with the stability and later fragmentation of Pangaea. As the continents remained largely unified, ecological opportunities were vast, and niches for small to medium-sized reptiles abounded. The earliest dinosaurs were not yet the titanic predators or colossal sauropods familiar from later eras. They were modestly sized, often no larger than a human, yet they exhibited a remarkable combination of efficiency and versatility. Their diets ranged from opportunistic herbivory to small prey predation, and their physiology reflected a balance between metabolic efficiency and active mobility. These pioneering creatures roamed the uninterrupted landscapes, exploring rivers, floodplains, and forests, testing survival strategies that would define dinosaur evolution for millions of years. But even as dinosaurs began to carve out ecological niches, the forces of plate tectonics continued their slow, inexorable work beneath their feet. Mantle convection currents, heat flow, and lithospheric stress began to create rifts along the continental margins. As fissures widened and rift valleys deepened, Pangaea's once unified interior began to fragment. These geological processes, imperceptible to the reptiles themselves, set in motion opportunities for dispersal and diversification. The same vast land that had nurtured their initial evolution now offered pathways to new habitats, separated by nascent seas and emerging mountain ranges. The fragmentation of Pangaea was both challenge and opportunity. Early dinosaurs that once roamed hundreds of kilometers without obstruction now encountered varied topography and emerging climatic gradients. In equatorial regions, seasonal monsoons influenced vegetation patterns, creating pockets of dense forest and open floodplains. In higher latitudes, shifting weather patterns produced cooler climates and increasingly seasonal environments. Dinosaurs adapted, evolving new strategies for locomotion, foraging, and social behavior. Herbivorous species diversified in response to plant availability, while carnivorous lineages tracked prey across expanding territories. This dynamic landscape accelerated evolutionary experimentation, as isolated populations responded independently to local conditions, generating a proliferation of distinct species across the drifting supercontinent. As the first oceanic incursions penetrated rifts and new seas emerged, they created additional selective pressures and dispersal barriers. Narrow seaways, estuarine environments, and tidal flats provided both challenges and opportunities. Dinosaurs that thrived near coastlines adapted to variable moisture levels, periodic inundation, and shifting shorelines. Meanwhile, inland populations faced aridification, fluctuating food availability, and expanding deserts. The spatial heterogeneity introduced by early ocean formation encouraged allopatric speciation, allowing lineages to diverge while retaining the foundational adaptations that had enabled their initial success. The very motion of the planet sculpted the evolutionary paths of these creatures, demonstrating how life and geology were inextricably intertwined. Fossil evidence offers glimpses into this period of early dinosaur expansion. Remains of small, bipedal carnivores found in regions that would later become South America, Africa, and North America reveal similar anatomical adaptations, suggesting a rapid dispersal across the unified supercontinent. Skeletal structures indicate agility, endurance, and efficient metabolism, all hallmarks of a lineage poised to exploit a world in flux. Herbivorous counterparts, equally widespread, display adaptations for browsing and grazing on diverse vegetation, including specialized teeth and jaw mechanics capable of processing fibrous plant material. These anatomical features testify not only to survival but to a flourishing within a landscape still largely connected yet subtly transforming. As the continents drifted further apart, dinosaurs followed the slow, invisible currents of land movement. Continental drift, imperceptible on a human timescale but monumental over millions of years, became a conveyor belt for dispersal. Populations once contiguous were gradually isolated by widening rifts, shallow seas, and emerging mountain ranges. Some lineages adapted to entirely new habitats. Lowland floodplains became marshy wetlands, deserts evolved into dune seas, and mid-latitude forests shifted in composition due to changing rainfall and temperature regimes. Each environmental transition prompted evolutionary experimentation, favoring traits that increased mobility, dietary flexibility, and environmental tolerance. Dinosaurs were not passive passengers. Their physiology, behavior, and reproductive strategies interacted with the moving continents, ensuring that they not only survived but thrived amid tectonic upheaval. The spread of dinosaurs across drifting lands also had ecological ramifications beyond their own evolution. Their foraging behavior influenced plant community structures, seed dispersal, and the establishment of vegetation zones. Carnivorous dinosaurs shaped prey populations, exerting selective pressures that cascaded through ecosystems. In newly emerging coastal and inland environments, dinosaurs became keystone species, their presence structuring the biological communities around them. Even as the supercontinent unraveled, these creatures exploited the continuity of land and the opportunities created by fragmentation, expanding into niches that would later support the explosive radiation of their descendants. By the time Pangaea had begun to fracture into recognizable continental fragments, dinosaurs had established themselves as dominant terrestrial animals. Early lineages had radiated widely, adapting to a remarkable diversity of climates and habitats. The interplay of tectonic forces, oceanic incursions, and shifting climates provided a dynamic backdrop against which evolution operated. Dinosaurs were beneficiaries of a planet in motion, able to exploit both continuity and change, dispersal corridors and isolation, deserts and forests, rivers and nascent seas. The narrative of dinosaur expansion during this period underscores a fundamental principle. Life responds to planetary dynamics with ingenuity and resilience. The continent's slow drift, the opening of new oceans, and the creation of novel ecological gradients were all drivers of evolutionary opportunity. Dinosaurs, equipped with adaptations for mobility, metabolic efficiency, and behavioral flexibility, capitalized on these opportunities, setting the stage for the Mesozoic era, a time when they would dominate terrestrial ecosystems in forms and sizes unimaginable to earlier life. Even subtle geological changes influenced patterns of dispersal. Mountain building, erosion, and sediment deposition altered travel corridors. Rivers draining into newly formed seas provided pathways for freshwater species and influenced vegetation patterns, which in turn shaped herbivore populations. Dinosaurs tracked these changes with remarkable precision over evolutionary time, their populations expanding, contracting, and diverging in response to the shifting world beneath their feet. The combination of tectonics, climate, and biological innovation created a feedback loop, accelerating the emergence of new forms and strategies while maintaining continuity with the ancestral adaptations that had first enabled their rise. Throughout this process, the evolutionary trajectory of dinosaurs illustrates the intimate relationship between life and Earth's physical dynamics. They were simultaneously products of their environment and agents of change within it. Their spread across drifting continents demonstrates how continental reconfiguration creates both opportunities and constraints, guiding the course of evolution in ways that are subtle yet profound. Dinosaurs did not merely survive the shifting world. They harnessed it, riding the plates themselves into new habitats, encountering new challenges and leaving a legacy that would echo through the Mesozoic. In observing the rise and spread of these early dinosaurs, we witness the confluence of biology and geology on a planetary scale. The first true dinosaurs emerged in a stable yet subtly shifting supercontinent, diversified as continents began to drift apart, and adapted to the changing climates and landscapes shaped by tectonic forces and nascent oceans. Their story is one of mobility, innovation, and resilience, a testament to the capacity of life to respond to Earth's dynamic processes. By the time the continents had begun to assume more familiar positions, dinosaurs had established themselves across vast tracts of land, occupying roles as predators, herbivores, and ecological engineers. The drifting plates provided corridors for dispersal, isolation for speciation, and gradients for adaptation. In doing so, they set the stage for the Mesozoic's extraordinary diversity, laying the foundations for the spectacular evolutionary experiment that would captivate future observers millions of years later. The rise of dinosaurs on drifting continents is thus a narrative of motion, tectonic, ecological, and evolutionary. It is a story in which life and Earth are inseparable, where every rift, every emerging sea, and every climatic shift provides both challenge and opportunity. Dinosaurs became the first passengers of continental drift, spreading across the newly partitioned lands, adapting to a planet in constant transformation, and marking the beginning of an era in which they would dominate the terrestrial world for more than 160 million years. Across the sprawling mosaic of modern continents, subtle traces of an ancient supercontinent linger, etched into rock, embedded in fossilized bones, and woven into the patterns of Earth's oceans and winds. These remnants whisper of a time when North America, South America, Africa, India, and Antarctica were fused into a single colossal landmass, a world known as Pangaea. Though hundreds of millions of years have passed, and oceans have claimed the gaps that once connected these lands, the scars of that unity remain, waiting for those who listen closely enough to hear their enduring story. The most visible of these ancient markers are mountain ranges that stretch across continents as if daring us to imagine their primordial alignment. The Appalachian Mountains of North America rise from the eastern United States, their roots plunging deep into crystalline rock formed during the collision of continental blocks. Across the Atlantic, the Atlas Mountains in northwest Africa mirror the Appalachians in both age and structure, their folds a testament to the immense forces that once compressed and deformed the Earth's crust during Pangaea's assembly. Geologists have traced these ranges' formation to the same tectonic events that welded the supercontinent together, and their continuing erosion is a slow echo of that primeval struggle. Each ridge and valley carries the memory of continental collision, recording in stone a drama that unfolded over tens of millions of years. Fossils provide a more intimate biological link to Pangaea. In South America, in regions now separated by thousands of kilometers of ocean from Africa and India, paleontologists have uncovered identical or closely related species that could only have spread across contiguous land. Reptilian fossils, amphibians, and early plants tell a story of unrestricted migration. For instance, the fossilized remains of the mesosaur, a freshwater reptile, appear in both southern Africa and eastern South America, indicating a habitat that spanned regions now divided by the South Atlantic. Similarly, glossopterid plants, whose leaves are found in South America, Africa, India, and even Antarctica, provide botanical evidence of a shared ecosystem that thrived across the supercontinent. These organisms could traverse vast landscapes without encountering the barriers posed by modern oceans, dispersing, evolving, and interacting in ways impossible once Pangaea fragmented. The patterns of ancient river systems, preserved in sedimentary deposits, further reveal the supercontinent's influence on Earth's geography. In many places, these deposits indicate long, meandering waterways that once carried water, sediment, and life across hundreds, even thousands of kilometers. Fossilized riverbeds, sediment layers, and mineral deposits illustrate the connectivity of Pangaea's interior, showing how freshwater ecosystems provided corridors for migration, feeding, and reproduction. Dinosaurs, early reptiles, and amphibians relied on these networks, moving from river valley to floodplain, from inland basin to coastal margin. The echoes of these paths remain detectable today in stratigraphy, isotopic signatures, and the alignment of mineral layers, offering a geological roadmap of the supercontinent's vascular system. Even the oceans carry memory of Pangaea's past. The very shape of the Atlantic and Indian Oceans, their currents, and the distribution of marine sediments all reflect the slow breakup of the supercontinent. As rift valleys widened and seawater flooded newly forming depressions, oceanic circulation patterns were forced to reorganize. Today, the Gulf Stream, the Agulhas Current, and the monsoonal patterns across the Indian Ocean retain subtle fingerprints of continental drift. The paths of warm and cold currents, their interaction with the atmosphere, and the resulting climatic zones echo the positions and movements of land masses that separated long ago. Oceanographers studying these patterns can trace the influence of Pangaea's fragmentation on both the circulation of water and the distribution of nutrients, showing that the memory of unity persists even in the dynamic, restless oceans. In addition to mountains, fossils, and oceans, ancient fault lines and rift zones preserve geological evidence of Pangaea's assembly and dispersal. Across Africa, South America, and Antarctica, linear features in bedrock mark the former locations of sutures, the lines along which continental blocks once joined. These zones, now hidden beneath soil, ice, or sediment, record immense stress, folding, and shearing. In places, mineral veins trace the paths of molten rock forced upward during tectonic collisions. These features not only record past collisions but also influence present-day geology, determining earthquake-prone zones, the location of natural resources, and even groundwater flow. The landscape itself, shaped by the assembly and later rifting of Pangaea, continues to influence human civilization, agriculture, and settlement patterns. Paleoclimatic evidence also preserves Pangaea's shadow. Cold deposits, glacial striations, and isotopic ratios reveal the environmental extremes that existed on the supercontinent. In parts of Gondwana, now southern continents, glacial deposits indicate ice sheets that once pressed down on the land, sculpting valleys and striations in the bedrock. In equatorial regions, coal and sedimentary deposits suggest lush, swampy environments, supporting dense forests that hosted diverse fauna. These patterns demonstrate the breadth of climates across a single landmass and reveal the extent to which the distribution of temperature, precipitation, and ecosystems was governed by geography. Modern scientists can read these signs to reconstruct ancient climates, understanding how life adapted to heat, cold, aridity, and humidity within a supercontinent that spanned nearly pole to pole. Even small-scale fossil evidence tells a compelling story. Insects trapped in amber, seeds encased in rock, and tiny vertebrate bones all provide clues about connectivity. The same species appear across continents now divided by oceans, proving that these regions were once linked and shared similar ecological communities. Paleontologists have uncovered remarkable cases of convergent evolution, where isolated populations adapted similarly to environmental pressures, hinting at a shared ancestral habitat before continental separation introduced geographic barriers. These findings highlight the continuity of life across Pangaea and how its breakup initiated evolutionary divergence that would later shape the Mesozoic and beyond. Moreover, modern ecosystems and ocean currents continue to carry traces of Pangaea's influence. The distribution of marine sediments along continental margins, the pathways of tropical cyclones, and even patterns of monsoon rainfall reflect the ancient positions of landmasses. By studying isotopes in ocean cores and sediment layers, scientists can detect the lingering effects of continental drift on the chemical and thermal structure of the oceans. In essence, the breakup of Pangaea left an imprint not only in rock and fossil but also in the rhythms of wind, waves, and climate that continue to circulate around the globe. The story of Pangaea is also inscribed in the deep crust of the continents. Seismic imaging and drilling have revealed remnants of ancient continental cores, called cratons, that formed the backbone of the supercontinent. These cratons, stable and ancient, resisted erosion and deformation while surrounding regions flexed, collided, and rifted apart. They form the geological memory of Pangaea's original structure, anchoring continents and influencing the pathways of rivers, the formation of mountain ranges, and even the locations of mineral deposits. Studying them allows geologists to reconstruct the supercontinent's configuration with remarkable precision, revealing the continuity and breakup sequence that shaped Earth's modern continents. The combination of geological and biological evidence paints a coherent picture. Pangaea was not merely a historical curiosity but a profound influencer of Earth's evolutionary trajectory. Its unity allowed species to roam freely, facilitating dispersal, competition, and adaptation on a planetary scale. Its breakup introduced isolation, leading to speciation and the emergence of modern biogeographical patterns. The evidence is preserved in mountains, fossils, rivers, ocean currents, and climatic patterns, all of which retain the faint memory of a world that no longer exists. Even in the human era, the echoes of Pangaea continue to inform our understanding of Earth. Oil and coal deposits, the distribution of aquifers, and the location of fertile soils are all shaped by ancient continental configurations. Archaeologists and paleontologists alike rely on knowledge of Pangaea's structure to contextualize fossil finds, track evolutionary lineages, and predict the locations of untapped resources. In studying the remnants of Pangaea, we do not merely glimpse the past. We understand how deep history continues to shape the present, influencing everything from climate patterns to ecosystems and natural resources. From the lofty peaks of the Appalachians to the sweeping deserts of Africa, from glacially scarred landscapes in Antarctica to tropical forests in South America, the fingerprints of Pangaea remain. Fossils trace the migrations of ancient species, rocks record tectonic collisions, and the oceans carry the memory of vanished continents. These hidden scars, imperceptible to the casual observer, persist as enduring evidence of Earth's grand, dynamic history, a history in which landmasses fused and fractured, life adapted and dispersed, and the rhythms of geology and biology intertwined to create the world we inhabit today. By following these geological and biological clues, we begin to perceive the supercontinent not as a static relic of deep time but as a living, dynamic influence whose effects ripple into the present. Pangaea's unity and its eventual fragmentation shaped the evolution of life, dictated the pathways of rivers and winds, and left indelible marks on the crust of the earth. In every fossil, in every fold of rock, and in every pulse of ocean current, the memory of Pangaea whispers of a time when the continents were one, inviting us to read, to imagine, and to marvel at the extraordinary story recorded across the globe. Earth's surface is never still. Beneath our feet, the mantle churns in slow, relentless currents, shifting continents, bending mountains, and carving oceans. The story of Pangaea, with its assembly and eventual breakup, is only one chapter in a vast, cyclical drama that has repeated countless times over the eons. As we observe the drift of today's continents, it becomes natural to ask, could Earth's continents reunite again? Might there be a future supercontinent, waiting in the deep reservoirs of time, just as Pangaea once rose from scattered lands to dominate the planet? The concept of supercontinents is embedded in the geological memory of Earth. Long before Pangaea existed, earlier supercontinents rose and fell in their own majestic cycles. Rodinia, forming roughly 1.1 billion years ago, was a landmass that stretched across much of Earth's surface, uniting modern-day Africa, North America, South America, Australia, and parts of Asia. Rodinia's formation, driven by mantle convection and plate collisions, had profound effects on climate, ocean circulation, and biological evolution. Its breakup created rift basins that would eventually give rise to the oceans and continents we recognize in later eras. Following Rodinia, the landmass of Pangaea appeared approximately 600 million years ago, forming a transient supercontinent whose existence was brief yet pivotal, setting the stage for the Cambrian explosion and the diversification of complex life. Each of these cycles demonstrates a natural rhythm: assembly, dominance, fragmentation, and dispersal, a planetary heartbeat visible only across geological timescales. Today, the continents continue their inexorable drift. North and South America pull away from Europe and Africa along the mid-Atlantic ridge, while the Pacific plate slowly consumes oceanic crust, drawing Japan, the Philippines, and the Western Americas closer to one another. Australia slides northward, aiming toward Asia, while India collides with Asia, raising the Himalayan mountains, a visible testament to ongoing tectonic activity. These movements, measured in mere centimeters per year, hint at a future where the scattered continents may once again converge. Geologists refer to this as the supercontinent cycle, a framework suggesting that every 300 to 500 million years, Earth's landmasses may assemble into a single unified entity. The mechanics of this cycle are governed by the deep forces of the mantle. Heat from the Earth's interior rises, creating convection currents that drag tectonic plates across the surface. Zones of subduction pull oceanic plates into the mantle, while ridges push newly formed crust outward. The dance is slow but inexorable, a choreography that has repeated over billions of years. As current plates continue their movement, future collisions are inevitable. Models of Earth's tectonic evolution predict potential configurations, each with different possibilities for how continents might come together. One scenario, called Amasia, envisions the Americas drifting northward to meet Asia around the North Pole, creating a vast polar supercontinent. Another, Nova Pangaea, imagines the Atlantic closing while the Pacific widens, bringing Africa, Europe, and the Americas into a massive central landmass. A third scenario, Pangaea Proxima, speculates that the continents could rotate back toward the tropics, forming a supercontinent reminiscent of the ancient Pangaea but with entirely new ecological and climatic arrangements. The recurrence of supercontinents is not merely theoretical. Geological evidence confirms that Earth's crust has repeatedly coalesced and broken apart over deep time. Rodinia, Pannotia, Pangaea. Each formation left indelible signatures in mountain ranges, fault lines, and sedimentary basins. Their assembly altered ocean currents, climate patterns, and the distribution of species. For instance, the merging of continents created vast interior deserts and reshaped rainfall patterns, influencing the evolution and distribution of terrestrial life. Conversely, their fragmentation allowed isolation, promoting speciation and the rise of new ecosystems. Recognizing these patterns allows scientists to extrapolate into the future, imagining the biological, climatic, and geological consequences of a yet-to-come supercontinent. The timing of future supercontinent formation is constrained by current plate velocities and tectonic trends. Presently, the Atlantic Ocean continues to widen at approximately 2 to 5 centimeters per year, slowly pushing the Americas further from Europe and Africa. Simultaneously, the Pacific Ocean is contracting, its plate subducting beneath surrounding continents. These dynamics suggest that over the next 200 to 300 million years, the configuration of Earth's landmasses will look dramatically different from today. Australia's northward journey, India's ongoing collision with Asia, and the shifting African rift zones all contribute to a slow but inevitable convergence. While the details remain speculative, the patterns of past supercontinent cycles provide a reliable template. The Earth's lithosphere is engaged in a perpetual rhythm of assembly and dispersal. Biological implications of a future supercontinent are profound. The merging of isolated continents would reconnect ecosystems long separated, enabling species migration on a massive scale. In the past, supercontinents facilitated the spread of plants and animals across vast territories, erasing geographic barriers and creating new opportunities for competition and adaptation. Future reunifications could similarly reshape biodiversity, introducing species to novel habitats, altering evolutionary pressures, and potentially triggering new adaptive radiations. Yet, just as in the past, the initial upheaval would likely generate ecological stress, with climates shifting in response to changed wind patterns, ocean circulation, and continental interiors. Interior deserts could expand, coastal areas might flood, and mountain building could create rain shadows, all influencing the survival and evolution of life on Earth. Climate would be transformed in ways both predictable and surprising. The assembly of a supercontinent concentrates landmass, altering global wind patterns and ocean currents. Interior regions, distant from the moderating influence of oceans, would likely experience extreme temperature fluctuations, scorching summers, bitter winters, and intermittent monsoonal rains. Coastal regions would encounter new tidal regimes, storm patterns, and sea level dynamics. The movement of continents toward the poles or equator would redefine latitudinal temperature gradients, influencing atmospheric circulation and precipitation patterns. Historical supercontinents provide a model for these changes. Pangaea's vast deserts, monsoonal systems, and polar ice distributions reveal the intricate interplay between geography and climate. In a future supercontinent, these interactions would once again sculpt the environmental canvas upon which life must adapt. Geologists also anticipate that the formation of a new supercontinent will leave telltale structural evidence in the crust long before the landmasses fully converge. Rift valleys, subduction zones, and volcanic arcs will mark the edges of approaching plates. Mountain ranges will begin to rise as crust is compressed, folded, and uplifted. These nascent features, detectable through seismic studies and satellite imagery, will foreshadow the eventual unification of continents. Just as Rodinia, Pangaea, and Pangaea left deep imprints in rock, so too will future configurations leave enduring records for scientists of a distant age. Even in the absence of living observers, Earth's crust will archive its movements, allowing future geologists to reconstruct the slow, deliberate choreography of continental drift. The philosophical reflection is equally compelling. Earth's history is a narrative of unity and fragmentation, of connections forged and broken, of life responding to ever-shifting landscapes. Pangaea, though long gone, reminds us that isolation and cohesion are temporary states in a dynamic system. Continents are not fixed. They are participants in a cycle larger than human observation, a rhythm that has persisted for billions of years. Life has adapted to these cycles before, exploiting openings, migrating across new corridors, and evolving in response to shifting climates and habitats. The rise and fall of supercontinents is thus both a geological and biological story, intertwining the inanimate forces of the mantle with the animate resilience of living beings. As we imagine a distant future where Earth's continents might once again unite, the reflection deepens. Once the planet was a single world, alive with connections across sprawling lands. Then oceans divided that unity into many worlds, each with its own ecosystems, climates, and evolutionary paths. In the vast temporal horizon ahead, those many worlds may again converge. Perhaps North America and Asia will meet at the pole, Africa will embrace South America, and Australia will reclaim a position near the equator. The Earth's rhythm, imperceptible in a human lifetime but persistent over geological time, ensures that the story of supercontinents will continue. Life, ever adaptive, will respond, migrate, and evolve. Mountains will rise, oceans will shift, and climates will transform, all under the patient, inexorable guidance of Earth's mantle. Speculation about a future supercontinent is not merely a scientific exercise. It is an invitation to witness Earth's grand narrative. The cycles of unity and fragmentation remind us that the world is dynamic, ever-changing, and profoundly interconnected. The continents we walk upon are neither permanent nor static. Their present configuration is temporary, a fleeting arrangement in a continuum of assembly and dispersal that has shaped the course of life and will continue to do so. The notion that Earth may once again form a supercontinent encourages a perspective that transcends human time, situating our existence within the deep, unfolding history of the planet. In contemplating this distant horizon, we recognize a paradox. Earth's surface can be both fragile and enduring. Oceans will rise and fall, mountains will erode, species will come and go, yet the mantle's relentless currents endure, guiding continents in their slow waltz. The memory of Rodinia, Pangaea, and Pangaea persists, not only in rocks and fossils but in the very patterns of movement that govern today's plates. They hint at what may come, a future where the continents once again unite, crafting a supercontinent whose landscapes, climates, and ecosystems remain beyond our imagination, yet whose formation is as inevitable as the forces that built the last one. Thus, as we survey the Earth of today, its drifting continents, restless oceans, and dynamic climate, we glimpse the prelude to a story yet unwritten. The supercontinent cycle continues, indifferent to human observation but intimately shaping the context of life on our planet. The Earth, once a single world, divided into many, may and eons yet to come converge again. And in that distant epoch, mountains will rise, seas will divide and join, ecosystems will adapt, and life will continue its unbroken saga. The cycle of assembly and fragmentation endures, a testament to Earth's persistent, patient dynamism. The future supercontinent, like those that preceded it, will serve as a stage for the drama of life, a vast arena where evolution will play out anew, where climates will challenge adaptation, and where continents will once more be bound together by the deep, invisible forces of the mantle. Perhaps the Earth will again experience the unity of a singular landmass, the interconnectedness of species, and the geological grandeur of continental convergence. Until that time, the continents will continue their slow dance, tracing the invisible rhythm of supercontinent cycles, and reminding us that in the vastness of geological time, nothing is permanent, yet everything is interconnected. Earth is a restless planet. Beneath the surface, forces older than life itself stir, shaping landscapes, directing oceans, and orchestrating the slow, unrelenting waltz of continents. As we reflect on the story of Pangaea, the singular supercontinent that once bound Earth's land into a seamless expanse, we are reminded that change is the only constant in the planet's grand narrative. Mountains rise and erode, oceans expand and contract, climates shift, species emerge and vanish. These are not exceptions but the rhythm of Earth's existence. In the quiet moments when we consider the immensity of geological time, we begin to perceive our place. Fleeting, ephemeral, yet intrinsically connected to the deep history of our world. Pangaea, forming roughly 335 million years ago and beginning its disintegration around 175 million years ago, offers a profound illustration of the planet's persistent dynamism. It was a single colossal landmass stretching across latitudes from pole to pole, merging what would become nearly all modern continents. Its assembly was driven by the relentless motion of tectonic plates, propelled by heat from the Earth's interior, manifesting in collisions, uplifts, and the creation of vast mountain ranges. The convergence of land masses created new habitats, shifted climatic zones, and reshaped oceanic currents. Life adapted, flourished, and in some cases suffered catastrophic decline, as the planet's energies remolded the surface. The story of Pangaea is not simply a tale of land masses colliding. It is a window into the deep patterns of change that have always governed Earth, a reminder that the ground beneath our feet is anything but stable. When we look at Pangaea, we see more than geological formations. We see the profound implications of continuity and disruption. For millions of years, species roamed without the barriers imposed by oceans, exploring vast expanses of connected land. Forests stretched uninterrupted, rivers carved long arteries through the terrain, and winds carried dust and moisture across continents with unprecedented reach. Yet, despite these periods of stability, the forces beneath ensured that nothing remained permanent. Mantle convection currents, subduction zones, and rifting continuously applied pressure, shaping the very crust we inhabit. Pangaea's eventual breakup into separate continents, the Atlantic opening, India drifting northward, Africa stretching, was an inevitable outcome of these enduring processes. The lesson is clear. Change is intrinsic, not episodic, and the Earth's story is a continuous, unbroken sequence of transformation. From a human perspective, the timescales involved are almost unimaginable. The lifespan of Pangaea spanned hundreds of millions of years, dwarfing the entirety of human history. Civilizations rise and fall in mere millennia, yet here we are, glimpsing only the final moments of continents that once sprawled as a single supercontinent. The land beneath our feet carries the memory of tectonic collisions, of molten rock and searing heat, of glaciations that sculpted valleys, and of forests and deserts that supported creatures no longer alive. Fossils buried deep in sedimentary layers tell stories of species that lived and died during this era. Amphibians, reptiles, early synapsids, and insects whose wings span forests vast and unknown. Each imprint in stone is a whisper from deep time, a reminder that life and land are inseparably intertwined, and that our own fleeting existence is but a small note in a symphony that has been playing for eons. The legacy of Pangaea extends far beyond the fossil record. Modern mountains, such as the Appalachians and the Atlas Range, bear the scars of ancient collisions that united continents into a supercontinent. Sedimentary deposits on multiple continents reveal traces of rivers and deltas that once flowed across continuous land. Ocean currents today still echo patterns established by the opening and closing of seas, shaped first by Pangaea's vast presence and later by its breakup. Even climates bear subtle imprints of that ancient unity. Seasonal winds, monsoonal patterns, and rain distribution reflect the deep memory of a time when a single landmass controlled the balance of atmosphere and ocean. To consider Pangaea is to recognize that the Earth remembers its own past, that it carries forward patterns established millions of years ago, and that the forces shaping life today are continuations of processes begun long before humans walked the planet. Pangaea also challenges our perception of scale. The enormity of this landmass, stretching thousands of kilometers in every direction, is difficult to truly imagine. It was a world without modern boundaries, where ecosystems intermingled freely, where evolutionary pressures unfolded across unprecedented distances, and where climatic extremes shaped the fates of countless species. The formation and eventual fragmentation of Pangaea demonstrate that stability is temporary, that cohesion can give way to division, and that the forces governing the Earth operate on scales that dwarf individual lifetimes. Human civilization, by contrast, is a momentary phenomenon, a brief flicker against the canvas of deep time. Our cities, roads, and fields are transient, destined to be altered, submerged, or transformed by the relentless pace of geological and climatic processes. Recognizing this perspective fosters humility and awe, reminding us that our concerns, though immediate and pressing, are minute when compared to the vast temporal rhythms of the Earth. Yet within this vastness, we find continuity and connection. The story of Pangaea is not merely a tale of loss or disappearance but of persistence and inheritance. Life that survived the breakup of supercontinents evolved in response to the new landscapes, filling ecological niches, adapting to emerging climates, and setting the stage for future evolutionary radiations. Dinosaurs, mammals, and myriad other lineages owe their existence in part to the legacies of Pangaea. The mixing of species, the creation of deserts, rivers, and coastal plains, and the isolation that followed the fragmentation of continents. In this way, Pangaea's story is both a record of destruction and a chronicle of opportunity. It reminds us that even amidst profound change, continuity persists and life, resilient and adaptive, endures. This reflection extends to humanity. Our brief tenure on Earth coincides with a period of relatively stable continental positions, moderate climates, and abundant resources. Yet even within this seeming stability, the mantle below continues its slow, inexorable work. The supercontinent cycle will resume, oceans will open and close, and landscapes will shift in ways beyond our imagination. Our presence, though momentary, is a continuation of Earth's story, a small but conscious thread woven into the ongoing tapestry of life and geology. By observing the deep rhythms of the planet, we gain perspective. Our triumphs, our struggles, our civilizations are part of a larger, ongoing process that spans billions of years. Moreover, Pangaea invites a meditation on time itself. Human perception is limited, bounded by years, decades, and centuries. Geology, by contrast, moves in millions, billions, and tens of billions of years. To study the supercontinent is to step outside the human scale, to witness the slow waltz of tectonic plates, the gradual rise of mountains, the formation of oceans, and the shaping of climates. It is to recognize that our species, though innovative and adaptive, is a brief actor on a stage far grander than ourselves. In acknowledging this scale, we cultivate both humility and wonder, recognizing that while individual lives are fleeting, they occur within an enduring and intricate planetary rhythm. The narrative of Pangaea also illuminates the interplay between stability and disruption. For hundreds of millions of years, the supercontinent existed as a continuous landmass, yet beneath its surface, forces of tension, compression, and convection were already at work. Its eventual breakup was not sudden but the result of pressures accumulating over eons, of fractures forming, rifts deepening, and mantle currents rising to tear the land apart. In the same way, the Earth today appears serene, yet the forces shaping continents, oceans, and climate continue their patient work. Recognizing this reminds us that apparent stability is always provisional, that the world is in constant motion, and that life, including our own, exists within a dynamic system far larger than our immediate perception. Pangaea's story is a testament to the Earth's memory. Mountains, valleys, rivers, and coastlines all carry traces of past configurations, a geological palimpsest etched in stone. Fossils, sedimentary layers, and mineral deposits record the climates, ecosystems, and species that once thrived. Even the present arrangement of continents hints at past connections, revealing a deep continuity across time. By studying these remnants, we connect with events that occurred long before humans existed and gain insight into the processes that will continue long after we are gone. In this sense, Pangaea is not merely history, it is a living framework, a lens through which we can understand the present and anticipate the distant future. Ultimately, contemplating Pangaea encourages reflection on human temporality. Our lives, though meaningful and consequential on personal scales, are ephemeral within the vast narrative of Earth. Civilizations, cities, and species themselves are transient. Yet, in our consciousness, we participate in the act of witnessing, of understanding, and of connecting with the planet's deep rhythms. The mountains we climb, the rivers we traverse, the forests we explore, all are part of a continuum that extends far beyond human memory. The story of Pangaea situates us within this continuum, highlighting both our fleeting presence and our intimate connection to the living, evolving Earth. This awareness brings both humility and wonder. We are, in geological terms, brief observers, yet we possess the unique capacity to reflect on the processes that shape our world. By acknowledging the deep time of Pangaea, we recognize that our actions, though momentary, occur within a much larger framework. The rhythms of the Earth, tectonics, climate, ocean circulation, and biological evolution, continue inexorably, indifferent to human presence. Yet our consciousness allows us to perceive, document, and appreciate these rhythms, to find meaning in the continuity and change that define our planet. The supercontinent reminds us that life, landscapes, and climate are interconnected. Species migrations, extinction events, and evolutionary radiations are all influenced by the positions of continents, the flow of oceans, and the patterns of climate. Mountains and valleys, rivers and coastlines are not merely static features but active participants in Earth's narrative. Pangaea's assembly and breakup demonstrate that Earth is a system of interlinked processes, a planet in constant dialogue with itself. Humanity, though brief in presence, is part of this dialogue, capable of observing, understanding, and influencing, yet always bounded by the deep temporal currents of the planet. As we consider our place within this vast story, we are invited to reflect on continuity and impermanence. Pangaea rose and fell, oceans expanded and contracted, species thrived and vanished. The land we inhabit today carries the memory of those distant epochs, yet it too will change, reshaped by forces that operate far beyond human timescales. Recognizing this, we cultivate a sense of respect and stewardship, appreciating that our actions occur within a living, dynamic Earth whose history is measured in eons. We are temporary inhabitants of a planet that remembers, evolves, and endures. In the end, Pangaea is more than a geological phenomenon, it is a philosophical lens. It teaches us that change is inevitable, that stability is fleeting, and that the rhythms of the Earth extend far beyond the limits of human perception. The supercontinent's legacy is present in every mountain range, every wind-swept desert, every river, and every living being that still traverses the surface of our planet. Our moment, though brief, is intimately connected to this deep history, a single chapter in a story that began long before us and will continue long after we are gone. By reflecting on Pangaea, we glimpse the vast scales of time, the forces that shape the Earth, and the transience of human life. We understand that the planet is never still, that change is the rule, and that continuity and transformation coexist in a delicate balance. In this awareness, we find humility, perspective, and a profound appreciation for the dynamic, living Earth. Our presence is fleeting, yet in witnessing and understanding, we participate in the ongoing story, connecting the present with the deep past and the distant future. Pangaea reminds us that Earth is alive in its own temporal dimensions, a planet in constant motion, a storyteller of eons. Mountains remember collisions, rivers recall ancient flows, and species bear the marks of evolutionary journeys across connected continents. As we consider our place within this grand tapestry, we recognize the beauty of impermanence, the inevitability of change, and the enduring rhythms that govern life and land. Time extends far beyond our lifespans, yet through observation, reflection, and understanding, we become participants in a story that has always been and always will be larger than ourselves. Close your eyes and let the Earth unfold before you, not as a map of borders or a collection of nations, but as a living, breathing being, ancient and patient, whose memories stretch back millions, even billions of years. Feel the pulse of time beneath your feet, subtle yet inexorable, like a slow heartbeat echoing through the crust, through the mountains and valleys, through the forests that once blanketed continents long before humans walked this world. The land remembers even if we forget. Every fold in the rock, every curve of a river, every glimmering coastline holds stories older than our imagination, stories of supercontinents joining and breaking apart, of oceans swallowing lands, of deserts and glaciers carving the shape of life itself. Imagine the vastness of Pangaea stretching across the planet, its core resting beneath your awareness, silently orchestrating climates, winds, and tides. The air carries whispers of ancient forests, the scent of rivers long vanished, the warmth of equatorial sun mingling with the icy breath of polar glaciers. You can feel the high oxygen skies above, where insects once cast enormous shadows across the canopy, and the roar of volcanoes that reshaped mountains and skies in a dance of creation and destruction. Every element, from dust carried by unbroken winds to the rhythmic flow of sprawling rivers, was part of an intricate choreography, a reminder that Earth's story is a melody of energy and patience, of destruction and renewal. Let your mind drift through the slow dance of tectonic plates. Beneath your consciousness, mantle currents ripple and convect, heat rising and sinking in a rhythm that has persisted since the planet's formation. These forces, invisible yet immense, guided the assembly of supercontinents like Pangaea, then their inevitable separation, sculpting oceans and mountain ranges, shaping habitats and the very climate that would determine the fate of countless species. The Earth moves not in haste, but with the measured grace of a storyteller who knows every word in every pause, every crescendo and quiet moment. Recall the giants of the past, dragonflies with wings stretching almost a meter, crawling arthropods whose bodies dominated the forest floor, creatures born of high oxygen and ancient adaptation. Imagine them moving through the air and among the trees, their existence a testament to the peculiar opportunities that a single unbroken landmass and a rich, vibrant atmosphere could afford. These evolutionary marvels remind us that life does not merely endure. It experiments, it stretches the boundaries of possibility, and it leaves traces that echo across millennia. Even as we walk the earth today, we walk in the shadow of these histories, connected by the shared struggle of survival and adaptation. And yet, the earth is also a patient teacher of impermanence. The Great Dying, the Permian Triassic extinction, swept through ecosystems like a wave of change, leaving only the most adaptable, the most resilient, to inherit the transformed world. Witness in your imagination the survivors carving new niches, small mammal-like creatures scuttling underfoot, early reptiles sunning themselves on warm stones, hardy plants taking root in soils reshaped by fire, ash, and wind. Their resilience is a quiet reminder that even in the face of unimaginable loss, life continues, that continuity and renewal are woven together in the fabric of Earth's history. Feel the weight of time pressing gently against your awareness, and allow your thoughts to drift across oceans forming and expanding, continents drifting apart, the Atlantic breathing into being for the first time. Imagine the slow creation of new coastlines, shallow seas lapping against rocky edges, currents beginning to shape climate, and rainfall carving paths through forests and valleys. The planet transforms in ways subtle and grand, leaving traces of ancient supercontinents in mountains, in fossils, in oceanic basins. Every fold and fracture, every fossilized leaf and ammonite shell, is a whisper from deep time, evidence that continuity and change coexist, and that we are part of this ongoing story. Let your mind wander to the philosophical, to the questions that Pangaea and the Earth's deep history raise. How small, how brief is a human life when measured against the pulse of continents? What does it mean to inhabit a world that remembers, a world whose rhythms dwarf our own? Perhaps our awareness, our curiosity, our capacity to reflect, is itself a product of this deep time, a fleeting consciousness that momentarily perceives the slow, grand dance of tectonics, climate, and evolution. Consider the mountains, rivers, and deserts not merely as scenery, but as witnesses, as participants in a drama that has unfolded for hundreds of millions of years, and will continue long after our brief presence fades. Allow your thoughts to drift further into the delicate interplay of wind, water, and life. The ancient currents of air and the paths of rivers connect everything, as they once carried nutrients, seeds, and organisms across vast distances, binding ecosystems into a seamless whole. Even today, the echoes of those patterns remain in ocean gyres, monsoons, and seasonal rains. Close your eyes and imagine dust traveling thousands of kilometers, a river feeding the distant sea, a forest breathing with life once unbroken, and the earth, in its own patient rhythm, orchestrating these movements. This interconnectedness, visible in fossils, sediments, and climate, speaks to a profound lesson. Life and land are inseparable, and the planet itself is an active participant in the ongoing story of existence. Breathe deeply and slowly. Feel the surface beneath you, solid yet alive, a repository of eons. Imagine standing on a ridge formed by colliding continents, hearing the faint echo of oceans long vanished, sensing the presence of glaciers that carved valleys you now trace. Every heartbeat aligns with the subtle pulse of Earth, the gentle movement of its interior, the persistent shaping of its exterior. In this moment, recognize the continuity of life, the resilience of ecosystems, and the delicate balance that allows species, including our own, to exist. Now imagine a night sky over Pangaea, stars spinning slowly overhead as they do today. The constellations are familiar, yet the land below is different, yet connected to what will come. Volcanoes rise and fall, rivers snake through forests, winds carry seeds and dust, and the planet hums softly with energy. Let this image fill your mind with calm, a timeless awareness that extends beyond human scales, a gentle meditation on the fleeting nature of life and the enduring pulse of the earth. As you breathe in, feel the warmth of sunlight across ancient plains. As you breathe out, release the tension of modern life. Imagine standing at the edge of a continent that stretches from pole to pole, hearing the distant call of an insect or reptile, feeling the movement of air and water that connects all living things. Let your awareness drift across millions of years, across forests, deserts, mountains, and oceans, each connected by invisible threads of energy, evolution, and geology. Consider, too, the impermanence that Pangaea teaches. Oceans will encroach, ice will advance, mountains will crumble, and species will adapt, flourish, and fade. Yet each cycle is a note in the symphony of Earth, and even as humans move, build, and dream, we are participants in this ongoing melody, brief yet conscious, fleeting yet capable of reflection. The knowledge of deep time offers perspective. Our challenges, our joys, our fears exist within a context that is both humbling and liberating. Let your imagination roam across rivers and forests, across deserts and ice sheets, across mountains and seas. Picture the creatures that once inhabited these lands, their lives fleeting in comparison to the land itself, yet remarkable in their adaptation and resilience. Feel the air on your skin, the movement of water beneath your feet, the whisper of wind across the plains, and let this awareness soothe and calm, as the earth itself moves slowly, patiently, eternally. In this quiet reflection, recognize your connection to the planet. You are part of its ongoing story, a fleeting witness to rhythms that predate you and will outlast you. The mountains, the oceans, the winds, the forests, they carry the memory of Pangaea and all supercontinents before and after it. Their presence is a reminder that life, though ephemeral, is entwined with deep processes that span eons. You too are a thread in this tapestry, briefly conscious, briefly aware, and yet part of the vast continuum of Earth's existence. As the night deepens, allow the images of ancient rivers, drifting continents, towering forests, and sweeping deserts to fade slowly, leaving only the gentle pulse of Earth beneath your consciousness. Feel your breathing synchronize with the planet's rhythm, slow, steady, eternal. Inhale the calm, exhale tension, and imagine the quiet continuity of life stretching across millions of years. Rest in the knowledge that Earth endures, that change is constant yet measured, that life persists in cycles of emergence, adaptation, and renewal. Let this awareness fill your mind with peace, a soft surrender to the slow unfolding of planetary time. Imagine the supercontinents rising and falling, oceans forming and retreating, species evolving and fading, and recognize that in this vast continuum, your own consciousness is a fleeting, precious spark. And now, as you drift gently into the quiet of your own thoughts, carry the vision of Pangaea with you. The vast connected land, the flowing rivers, the winds that traveled unbroken, the creatures that roamed freely, and the patient, enduring pulse of Earth beneath it all. Let it lull you into calm reflection, a meditation on time, connection, and the beauty of impermanence. Good night, time traveler.